last-minute cancellations due to travel problems that people experienced. Big storms in Germany made it difficult to travel. So 2 of the contributed talks have been canceled, and that should be reflected. The schedule on the website is current, but you might see the schedules on the slides might be slightly out of date. But our next talk is the one that is shown here, Towards an Equational Calculus of Interventions. And great. So Shub, whenever you're ready. Shub Agrawal is going to tell us about an equational calculus of interventions. Great, thanks.
Hi, everyone. So I'm Shub from Northeastern, and I'm going to talk about our work towards an equational calculus of interventions. So first question, when you see the and we want to ask a question, which is to what extent does smokes, the variable in this program, cause cancer? And so the way we answer this is, like I said, we set the value of smokes, and the way we're going to do that is replace the mechanism that computes smokes with a free variable s hat, which represents this like act of setting the variable. And then we're only concerned with the impact on cancer, so we can throw away all those other returns. And then this is just an inference problem, and we can go ahead and solve it. We can sort of run inference twice, substituting true in for s hat or false in for s hat, and we'll get literally a number, and we'll get that maybe the probability of getting cancer if you smoke increases by 0.35. These are made-up numbers. I can't vouch for them. OK, so to relate this to some prior work in this area, here we have this full program. And studying interventions and causal queries in this setting is well studied by prior work like Omega and Cairo. And I think we're going to hear more about this later as well. But we want to generalize this somewhat. So the first change is that instead of having a specific mechanism, instead of knowing exactly what the program is, we might have unknown mechanisms. So we have some uninterpreted function that we know there's some relationship between the variables, but we don't necessarily know exactly what it is. The second generalization is the addition of what we call latent variables, or sorry, what are called latent variables. And this is where some variables, for example, genotype in this situation, we are assuming it's part of the causal mechanism, but we're not able to measure it. We don't even know what it exists or what genotype it is, and so we can't return it. And now we might ask the same question: to what extent does smokes cause cancer? And we do the same trick as earlier. We replace the mechanism that computes smokes, and we change the return value. But the problem is now this is no longer a program that we can run inference on. There's all these uninterpreted mechanisms. So the best we can do is estimate this by going to the real world. And what we would do is an experiment in the traditional sense. We would give half of the people cigarettes and tell them to smoke them, not give them to half the people, and that would correspond to this S hat. And then we would measure the impact on cancer. Now, like we said, that's unethical. Instead, what we might do is an observational study, which just looks at whether people are smoking or not. And also, we might look at this other variable, tar, which can sort of help us understand the link better. and that would correspond to an estimate of this original program that we had. Okay, but the problem is this is a completely different program and a completely different question. So why does having an estimate of that program help us? And this is where UDA-Perl's do calculus comes in. So what the do calculus says is when you have a distribution with a do in it, so do corresponds to this intervention that we were talking about, you can turn this into a do-free expression, so something that doesn't require any interventions and looks like normal pen and paper probability, with some series of equations. And these equations are what's called the do calculus, which was first introduced in 1995 by UDA-Perl. So our position is that these insights in do calculus and these equations can be applied to probabilistic programs as a typed equational theory. So what we mean by this is that this expression, the probability of C given do S, corresponds to these programs representing experiments like we had on the last slide. These the equations correspond to a typed equational theory, and we'll show an example of an equational rule. And this do-free expression corresponds to a program which uses the observational study as a subprogram. And the idea is that once we have an estimate of the observational program, and we have an estimate of that subprogram, then we can run inference to get an estimate of the program as a whole. And hopefully that will become clearer later as well. But before we talk about what that final program looks like, I want to talk about what some of these equational rules look like. And I'm going to talk about maybe the most important equational rule, which is called observation-intervention exchange. And this tells us when we can turn our interventional distribution, the probability of y given that we intervene on x, into a regular conditional distribution, like the probability of y given that we just observe x as normal. And the thing to point out, we've encoded this rule as what looks like the shape of a regular typed equational rule. And the things I want to point out here, so first of all, there's a major difference here, which is that our do calculus rule has the introduction of this other variable y, which is the effect, like the variable whose effect we're interested in. Meanwhile, our rule doesn't have that variable at all. Instead, we're just looking at the return value of x. And so in that sense, our rule is a little bit more local than the corresponding do calculus rule. There's another sense in which our rule is more local, which is that the do calculus rule has this global independence criterion as a premise. So this is that y is independent from x in the full global model. So that's what the do calculus rule looks like. Let's talk a little bit more about what our rule is. Our rule is talking about basically there are two ways to represent an intervention. So we start with this program E, which is a distribution, let's say a distribution over Booleans that has probability 0.3 of returning blue and probability 0.7 of returning green. One way of representing an intervention is throw away this original program that's computing it and return the value that we want to set the variable to. So in this case, green. And we'll get a Dirac delta distribution over green. The alternative way to do this is start with our same program and instead observe what its value is using conditioning. And this is going to give us a subdistribution. And then we have to normalize that distribution. And we, once again, are going to get a Dirac delta distribution. So hopefully it's intuitive that these two programs as sort of sub-expressions are equivalent. But like we said earlier, this is sort of a sub-expression. It's sort of local. And we're going to have to compose it with a bunch of other rules to turn it into, to get the full effect that we wanted earlier. So if we want to look at this final program that is able to finally simulate the intervention, it looks like this. So there's a lot of complex transformations that need to happen. I'll point out two things about this, and I'm happy to talk about this more later. But one thing is that our intervened variable s hat is used as a observation rather than as an input to anything. And it's not like it was in the original experiment. And the second thing is that we use this subprogram O, which represents our observational study. And we can see that this is the only unknown in the program. Everything else is just like a normal probabilistic program. And so we can do the same thing earlier of substituting in true and false for s hat and figure out what the answer is. And hopefully we would get the same answer. assuming we had some estimate for the distribution of O. So yeah, that's the crux of it. We want to turn programs representing experiments into programs which use observational studies that can simulate them. In future work, we want to work on automation for these equations. We want to work on some higher level reasoning that looks closer to what the do calculus does. And we also want to work on a semantic model that can help us to validate the equations. In the extended abstract, we have a full equivalence proof and equational rules. So I'm happy to talk about that and also during the poster session. And yeah, I'm also happy to take questions.
That great talk. We have time for a question or two.
Thanks for this work. This is something I've been thinking about, and that's super interesting. And I agree. This syntactic PL approach is very nice compared to how the do calculus is set up. My question is: do you have any indication of completeness? So you showed one equation, and it's never quite clear for me what the do calculus takes. And I bet it's not a lot. Like it should be a finite amount of equations. But do you have them?
Yeah, so in this work, we don't make any claims about completeness. We have this fully worked example that's sort of like, for the do calculus, supposed to illustrate all the features. So like, we think probably you could generate a complete set of rules, but we're not going to claim that the set of rules that we have right now is complete.
Great, and maybe as we take our next question, could the next speaker come up and prepare?
Thank you for the nice presentation. You presented this equivalence between intervention and conditioning. And I was wondering if you could give an intuition for the correspondence between. Are you familiar with the backdoor rule in the do calculus, and what would that correspond to in traditional probabilistic programming?
Yeah, so the backdoor rule is sort of this. It's sort of an illustration of when you have a confounding common cause. And I think what's weird about our rules is that it doesn't show up directly. The do calculus rule for the observation intervention exchange does directly have the backdoor criterion. For us, it sort of like falls out of the other rules that we have that look like normal probabilistic programming rules. And it sort of like falls out in the composition of these rules somehow. So it's sort of hard to like explain exactly where it is. So maybe better to talk about that offline.
Okay, thank you.
Next up, we have Thea Wong talking to us about type abstractions for causal probabilistic programming. Thanks.
Yes, so, okay. Hello, everyone. Welcome to my talk. So I'll be talking about typed abstractions for causal probabilistic programming. And just joint work with Dario, who is here, and as well as Eli, Jack, Ohad, Michael, and Jeremy. So I want to start by putting our work in some context, right? So causal inference, or causal reasoning in general, as already mentioned previously, is this mathematical toolkit developed by POPL to reason about causal relationships, like does X cause Y? Or given that we saw Y, had X not happened, would Y still have happened? So this toolkit has wide applications in empirical sciences and most recently machine learning and, well, in everything that really requires you to talk about causal relationships. Causal probabilistic programming is this programming paradigm that's developed quite recently, which involves extending a fully fledged probabilistic programming language with first-class causal primitives. So the idea is then to be able to perform causal inference on general probabilistic programs. So there's a couple of examples of languages that meet this description. including multiverse, omega C, as well as Cairo, which is the one we're going to focus on today. It's this Python library developed by Basis that I think was also mentioned briefly in the industry talk. And our contribution is that we made Cairo into a Haskell library. And that meant that we had to first disentangle its cool features from the implementation concerns, like well, it was implemented using Pyro's effect handlers and vectorization. And also it was in Python, so untyped, so we had to make all the abstractions typed. And by doing so, we have obtained a much clearer description of what its semantics looks like. And this is what our talk, this is what how this talk is going to be structured. So we'll start with the crash course in causal inference with a small example, and then we'll show you how to use typed abstractions to actually solve this problem in the Cairo style. So, right. Let's start with a small example. Say Dario has a car, right? And it's represented with, so the probability of it starting is represented by this probabilistic program. So it starts if it has fuel and battery, and it has fuel with probability 0.8, and independently it has battery with probability 0.9. So Dario is quite unhappy today because his car didn't start. And we want to ask, had he refueled, would the car have started? And the first thing we want to notice here is that this query is not quite a probabilistic query. You can't directly solve it with probabilistic programming because, well, firstly, this doesn't even talk about just one model. It talks about somehow two copies of the same model. We have a factual one where Dario's car didn't start, the real world, and a counterfactual one where we are asking if he had refueled, would the car have started? And in fact, what we're doing on the factual world is what's called observation. So it's the same, it's conditioning, right? In probabilistic programming, just saying, OK, we condition on the fact that Dario's car didn't start. But what we're doing on the counterfactual world is not observation. It's what's called an intervention. So intuitively, it means that we're not observing that Dario hasn't refueled. What we're doing is the equivalent of going back in time and forcing Dario to refuel his car while keeping everything else the same, and then asking, OK, would the car have started in this scenario? So how do we answer this kind of query systematically? Well, this is exactly what POPL''s toolkit is about. And the idea is to transform the original model that we have into another one, such that if you do inference on it, it will produce the answer to the causal query we're after. So we would be reducing the causal query into a probabilistic one. And so if we start with our original program at the top here, the first step we'd do would be twinning. So this is a program transformation, or like naturally presented as a program transformation, perhaps. And the point is that we want to create these two copies of the same world, right? While keeping everything else as much the same as possible. And this is exactly what twinning is about. And as you can see here, we have created, well, OK. No, I'm not going to use this mouth. So as you can see here, we have like two copies of the same model such that they are correlated in some appropriate way. In this particular case, the key attributes that we're sharing between the two worlds would be fuel and battery. And these would be called exogenous variable in POPL''s presentation. And then once we have this twinned model, all that we have to do is observing on the factual world and intervening on the counterfactual world. So this is what we get. Observing is easy, right? We know how to do conditioning, just add a statement at the end. But intervention is a bit more involved. You have to do this program transformation, where we have to find the counterfactual copy of fuel and then set it to true. So then if you look at what we have at the end, if you look at the model that we have at the end, then, well, this is basically what we expected. We have two worlds, a factual one and a counterfactual one. And then on the counterfactual one, we have intervened on fuel, but kept everything else the same. And so now if you run inference on it, you get about 64%, which is, by the way, the answer to the question that we had. Right. OK, so let's stop and think what we did here. We have reduced our causal query into a probabilistic one by successfully applying these program transformations, so these causal operations, on the original model. And in fact, all of the causal operations that we have given were presented as these program transformations, which is nice to some extent. But then also, program transformations are very subtle to deal with and don't necessarily compose very well. So we don't really want that. And what we want instead is to have a language that has these these causal primitives as first-class operations, such that we can perform these operations, these transformations automatically, but also in a way that is safe and compositional. And as you've guessed, we'll do this by having a typed version of Cairo, the probabilistic programming language developed by Basis. Right. So this is what the second half of the talk is going to be about. I'll give you a taste of what the abstractions are like. Okay. So, okay, firstly, let's think about how to implement these interventions, right? The idea is to, well, not allow interventions on arbitrary points of the program, but instead only allow them at these specific points we call intervention points. So these intervention points will be these program locations where we allow intervention to happen, right? And formally what we do is, well, we create this monad called the calls monad, which will represent all of the like the causal models. And this is basically, as you can see, a reader monad transformer on the probability monad. And this additional environment that we're taking here is should be thought of as this map in the programmatic sense from intervention points to lists of intervention instructions. What that means is that a model is now the suspended computation that is executed on an environment, and this environment contains for each intervention point all of the interventions that you're inserting in this program. So concretely in a model, this is what it looks like. So at line 5 here, we're creating this new intervention point for the original fuel value. And what this says is basically that, well, okay, this new operation creates this new intervention point. It takes an identifier called fuel point. And then what it does on this fuel value is that, well, it takes it, and then it reads from the environment, gets all of the intervention instructions that are associated to this intervention point, and then applies them on fuel. And fuel int is the return, like was what comes out of applying all of these interventions on fuel. And the good thing about presenting things this way is that instead of doing program transformations, we can just formulate the idea of inserting an intervention in a program as doing a transformation on the environment. And for example, here, like if we want to insert this intervention instruction at an intervention point, then all that we do is, well, we take an environment and insert it at the corresponding entry in the environment. And then to apply it on the model, all that we do is just pre-compose the model with it. So it all becomes very clear, and we don't really need to do any program transformation anymore. So what about twinning? So twinning is a bit more involved, actually, and we don't really have time to talk much into it. But basically what we're doing, like the strategy is to automatically perform twinning by eagerly computing all of the worlds that we are actually interested in at the same time. And the first question, of course, is, well, what worlds do we want to use? And basically those worlds will be determined by the interventions. Like, for example, if we have one intervention, then we're interested in 2 worlds, one factual, one counterfactual. If we have 2, we're interested in 4, etc. And then how we do this is by using an applicative called multivalue. I won't give much more detail in it, but yeah, come find me at the poster session or a bit later if you're interested. And right, if you put everything together, this is what the program would look like. To solve that exact same problem. And the point is that the model code here, the code here is very clean and simple, right? So the model is exactly what it was before, except we're threading through this this applicative to do the twinning automatically. And we'll also added on line 5 here an intervention point so that we can do the intervention on fuel. And then the inference is also very simple, right? So you take so basically what you're doing is, well, you take the model and then apply the intervention on the model here. And then once you have the intervention in the program, the twinning will be happening automatically. And all that you have to do is to get the factual value of whether the car starts and condition it to be false, and then return the counterfactual value. And now if you run inference on it, if you run inference on it, then you get exactly the right answer, which is about 64%. Right. So, okay, to conclude briefly, we've started by presenting these causal operations in Perl style as program transformations, but then we saw that actually we could do them automatically and safely using some typed abstractions that we created by taking inspiration from Cairo, where you have this interventions as a monad, a reader monad, and twinning as this applicative. And this is actually very highly expressive, as we have like a lot of examples in the implementation if you're interested. And this is also our first step towards giving a more general semantics to causal probabilistic programming. Yeah, so if you're more interested, I'm here at the poster session. Dario's also here, so yeah.
Thank you. For one question, and for the next speaker, please get ready.
Thanks for the talk. It looks like you still have a little bit of program transformation to do if you want to do intervention, where you have to add these points in the original program, right? The intervention points.
So to some extent, yes, but then
So the question is, could you just take all the random variables that are defined in your program and declare them as points? So you
Yes.
could intervene on everything.
yes,
And
you can intervene on any value at any point in the program,
Right.
like as long as you put an intervention point on it.
But that could be automatic, right?
Well, you could make it automatic if you want to, but then the point is also that, well, so if you want everything to kind of type check, you want that all of the holes that you're creating in the program to be typed holes, basically. And so the idea of intervention points is basically exactly this notion of a type hole. So we make users add these intervention points.
Thanks.
Thank you.
All right, great to be here. This is going to be somewhat of a shift in gear, so put your PLDI hats on. All right, yes, I'm Matin. I'm going to be talking about this design for doing high throughput GIP sampling on GPUs. It's work done with Martin Reinert and Vikash Mansinga at MIT. It focuses on GIP sampling. GIP sampling is a fundamental algorithm in probabilistic inference. It's an approximate sampling algorithm, and it has many applications in artificial intelligence, data science, bioinformatics, and many more fields. In fact, to the best of my knowledge, the first ever probabilistic programming language, Bugs, was introduced more than 30 years ago to do this, GIP sampling. And it's still somewhat maintained. And the latest version, I think, came out in 2020. Even though it's really popular, GIP sampling can only be done in like a limited class of models. It can be only done in Bayes nets whose variables satisfy certain conjugacy relationships, and we'll see why. But even then, it's very useful. I'm going to try to show that even for this very limited class of models, doing a good job of having a high throughput sampler on the GPU could still be kind of nuanced. But we first need to know what the challenges are and what the solutions are. So let's do a quick run through of GIP sampling. In this talk, I'm going to use this factor graph notation to denote graphical models, to show graphical models. A factor graph is just a graph with two types of nodes, variable nodes and factor nodes. And variable nodes we show with circles, factor nodes we show with squares. And the graph is bipartite. Circles only connect to squares and vice versa. The graph as a whole just represents a real valued function. The inputs to the function correspond to like these variable nodes. And they could essentially take arbitrary type. Here I've shown one with like 5 inputs, and they could all have a different type. And the function we assume factorizes into a product. And each factor in the product corresponds to a factor node in the graph. And the adjacency relationship in the graph denotes what variables participate in what factors. So here, for example, we can see that factor f6 contains variables x5 and x4 by just looking at the graph. OK, so how do we actually do GIP sampling in this notation? Well, we first start by assigning arbitrary values to the variables. Some arbitrary values have been assigned. And then we go over the variables in some order. So here I've started with like x1 as my first variable. What we do here is we fix all the other variables to the values that they have currently and resample x1
from a distribution whose density corresponds to like, the full density of the graph, but partially evaluated at everything else fixed. And we call this the Gibbs sampling distribution of x1. And here I've put it on this slide. Okay, once we've done this, we're going to go to the next variable, for example, x2 here, do the same exact thing for x2, sample it from a Gibbs sampling distribution by fixing everything else, then x3, and so on. And once we do this for all the variables once, this is called a Gibbs sweep. And as we do many Gibbs sweeps, the joint sample here, the sample of x1 through x5, converges in distribution to the normalized density denoted by the whole model. Okay, so one crucial thing to note here is that the Gibbs sampling distribution of each variable only depends on a subset of the entire set of variables. And the subset is the ones that participate in the factors that the variable under consideration participates in. So, for example, here for x4, we can see that if we write out the densities, the Gibbs sampling distribution of x4 only depends on x3 and x5 because it participates in factors f5 and f6, which are all the factors that x4 participates in. And this set of distributions, this set of variables, the set of variables that fully determine the Gibbs sampling distribution of a variable under consideration is called this Markov blanket. And here I've put it in blue, for example, for x4. Okay, so just to summarize, how do we do Gibbs sampling? We have a bunch of sweeps we need to do. For each one of the sweeps, we go over the variables. We first go gather the values of the variable under consideration, of the variables of the Markov blanket of the variable under consideration. We then partially evaluate all the factors that contain the variable, multiply them together, and we resample the value of the variable that we are considering by just normalizing that and sampling from it. And this, being able to go to this normalized product is why we need conjugacy relationships. Okay, I'm going to refer to these three stages at the inner loop of Gibbs sampling as the gather stage, the aggregate stage, and the sample stage. And we're going to use this terminology. Okay, so this brings us to the first big idea behind the design, is that if the Gibbs distribution of a variable only depends on the Markov blanket of that variable, then if two variables have disjoint Markov blankets, they could be sampled in parallel. And this is a well-known idea. It leads to this algorithm called chromatic Gibbs sampling. And chromatic is there because you do a graph coloring at some point. And to do that, you just create a simpler graph from the factor graph called the Markov random field graph by connecting any two circles that have a square neighbor. And by construction in this graph, two nodes are adjacent if and only if they participate in each other's Markov blankets. And so if I color this graph, do a vertex coloring of this graph, I get a partitioning of the variables into sets that each color can be sampled in parallel, essentially. All right, now we have the second observation, which is this is not enough if you want to do high throughput Gibbs sampling on a GPU. And to see why, I'm going to show you two kind of representative examples of the workloads that people use for Gibbs sampling. The first one is this friendly Ising model. If you look at it, you see that the factor graph for an Ising model is highly regular, and the Markov blanket of each variable is the same size and it's very small. So the sensible way to write a high throughput Gibbs sampler for this type of a model on the GPU is to just parallelize over the sets of variables that have disjoint Markov blankets, but then for each one of the variables, just serially do all the three stages and do the resampling. Now let's contrast that to this Bayesian mixture modeling kind of factor graph. Let's assume a Gaussian mixture model. You can see that this is a highly irregular graph. And the reason for that is typically in a mixture modeling problem, you have many more data points than you have mixture components. That's kind of the point of mixture modeling. And so if you wanted to do implement a high throughput version of this on the GPU, for these variables down here, for the variables that indicate what data point goes to what mixture, you would do the same as before. These have almost all the same degree and a small Markov blanket. So you do that part in serial. You parallelize over them, but for each one of the stages of the Gibbs sampling, you do them serially. But for the variables on the top, the ones that show the mixture component parameters, what you would want to do is you want to do the aggregation step in parallel as well, because otherwise, you're leaving throughput on the table. And so that brings us to the last big observation behind the design, is that because the parallelism will depend on the workload under consideration, you want it to be programmable. And so this makes our design very similar to languages like TVM or Halide, where a program doesn't only specify what computation needs to be done, but also at a high level of abstraction says, how should it be parallelized? And this is going to be the full design then. We start with a user-facing kind of BaseNet DSL. We lower it to a factor IR, which kind of lets us, the same way factor graph lets us read the factorization structure really easily. That allows us to do the same. And then using that, we could detect parallelism over variables using chromatic type techniques, or detect parallelism where parallelism can happen for aggregation. All of that is indicated in a schedule object. The schedule object could be tuned using dynamic analyses optionally, and then we use that finally to generate the final GPU code. And there's tons of details that go into this. I'm not going to go over the details. I'm going to do a shameless plug. Come to the poster and talk to me. I'd be excited to talk to you about it. The only thing I will briefly mention is the schedule object, partially because my review said that would be a good thing to talk about. The schedule object is a simple type of data structure. It has like a bi-level hierarchy. The first level of the hierarchy we call steps, and that just says what groups of variables should be sampled before the others. So even in like the chromatic case, you can think about each color is sampled in parallel, but the colors themselves are serialized. And so that's the first level of the scheduled data structure. The second level of the hierarchy is what we call streams. And streams indicate within each step what variables generate independent streams of instructions to be executed on the device. And essentially, this is just to accommodate the hardware. Lastly, we could tag some of these streams for whether the aggregation step should be done in parallel or serially. And with this sort of a scheduled data structure, we can write high throughput samplers for both the Ising example, for the mixture modeling example, and many more things. All right. That's all I had. Thank you for your attention.
Great. Time for a question or two?
Yeah, thanks. Maybe I missed the point entirely, but the schedule object, the goal is really for the user to interact with them. It's not because some part of it presumably is automatically generated by some chromatic.
Exactly. So the schedule object has essentially 2 points. One of it is like, if the user knows what to put in, it could partially put that in, and the rest is filled out by this chromatic thing, and etc. But also, once you have a reified schedule object, you could search over the space of schedules and do auto-tuning and dynamic analyses to like get even better performance based on the workload itself. Yeah.
Thanks.
Sure.
Maybe I'll ask a quick question while we get the next speaker, Karen, to come up. So do you know if there's been work on sort of like optimal chromatic or like what makes a coloring good for a chromatic Gibbs? And do you think, all of these other sort of fine-grained options in the schedule changes that at all?
Right. So the thing you want in the coloring is to have as few colors as possible, because colors kind of correspond to the serial stages. But graph coloring is like NP complete or NP hard or one of those. So I have some like experimental results there. I don't know if there's work on like optimal coloring, but I just use like a run-of-the-mill greedy coloring algorithm, and for like the typical benchmarks that people use and a bunch of like useful classes of models, I got small numbers of colors, so I'm happy. All right, thank you.
No, it is.
Should we go ahead? Hello. Yeah. Welcome back to Lafi, everyone. We now have a keynote session given by Dario Stein, who was until recently at Nijmegen. And so over many years, Dario's made, I think, some very important contributions to probabilistic programming, in particular theoretical and foundational questions. And so recently, he's been working on causal probabilistic programming, and so I'm very excited to hear what he has to say. Please go ahead, Dario.
Thanks, Hugo. So let's think back some hours to the beginning of Lafi. So when I looked at the program, before I looked at the program, I thought this would be titled an invitation or an introduction to causal probabilistic programming, because this is something new and exciting that I want to get you guys invested in. But then I saw that we already have like lots of talks and things on it. So I changed the title and now say, it's already here, right? Causal probabilistic programming exists, and I will give you a welcome. I will show you what it is about and what are interesting questions and interesting challenges. And because this is very new, there will be lots of questions and challenges, and there's more things that I don't know than things I know. So I'll show you some things that I know, I'll show you some things that I care about, and then hopefully we can kind of go forward together and explore this paradigm. This contains some joint work that I've been doing with these people. This is the same collaboration that already Theo's talk was about with Cairo people. Cairo is a causal probabilistic programming language built on top of Pyro. And I'll talk a tiny bit about this, but this is more kind of the broad context of what we want to achieve. What do we want to achieve? So causality, is the field that asks about cause and effect relationships. And I've been trying to come up with examples, but that's kind of understating it. Any finite list of examples would understate it, because this is the essence of science, right? This is in any empirical question. This is in the end what we want to know, right? What can we change? Does this cause that? And then a lot of kind of everyday statistics that we do is on an observational level. We talk about correlations and not causes, and we've been kind of taught to correlation doesn't imply causation, right? But then what is causation and what does imply it? That's the whole purview of this field. So there's some classical questions, right? Like does this drug work? If it works, why does it work? Is it a direct cause, or is there some weird side effect which is instead why it works? Does smoking cause cancer? Or like very relevantly something like how much of the snow chaos can be attributed to climate change? Or according to Theo, I have a car, right? But I've actually taken the train, which could have gone very badly. So if I had taken a plane, would I have arrived at Rennes? Those are causal questions, and we want to answer them. Now, interestingly, very recently, also machine learning has been getting interested in this causal paradigm. So there's some screenshot of a framework, PyY, that has different frameworks and languages and libraries to kind of explore causality. Now stuff starts to pop up with large language models, for example, where we ask about counterfactual tokens. So LLMs themselves are bad with causal reasoning, but of course internally it's a causal process. So we can ask, hey, we saw this token here, what would have happened if, I don't know, the story you're writing, the person has a different name, would have that, what would that have affected? So there's interest also in this, in kind of machine learning. And now, so to give you the broad overview, the study of causality goes back to Judea Pearl, and his famous 2002 book, Causality. And what he does is, first of all, give a mathematical theory of what these things mean, because before that causality was a bit shunned, right? It's like, it's philosophy, it's not really statistics, it's not something you can calculate. But he can calculate, and for this he kind of classifies causal queries into what he calls a ladder, and it has 3 different rungs. And the most basic rung here is rung 1, that is traditional statistics. So those are all the questions that deal with just observing a situation as it unfolds. And if we observe, we can look at, I don't know, distributions, we can look at correlations, all this kind of thing where we leave a system unperturbed. That's the seeing level, the observational one. So an observational question would be, is smoking associated with cancer? Okay, we just collect data and then we compute a coefficient and fine. There we have it. But that's not a causal question. The causal question we want to ask is, does smoking cause cancer? And we cannot answer this just with associational data, because there's many different causal structures that are imaginable, which are consistent with those observations here, but they tell very different stories once we intervene. Intervening means I force a person to smoke, and like, how does that affect their life? Again, very unethical, but this is the type of question that we're actually interested in. Or I give a patient a drug, or I don't know, make a person drink alcohol. What does that affect? That's very different from just seeing that people who happen to drink alcohol also have other outcomes. So this interventional rung 2 here is really where talking about causes starts. Okay, why do I have an arrow here? Because the higher rungs project onto the lower ones, right? So from any causal situation, I can also get observational predictions, but I usually cannot go up. So I have lots of situations here that are consistent with something higher up, but I don't necessarily know how to infer stuff here unless I make assumptions, and then I sometimes can infer, and this kind of lifting problem is exactly what causal inference is about. And then there's a third rung, which is counterfactual reasoning. So this is not just changing something, but this is having observed something and then kind of imagining what could have happened if things were different. And this is very human, this is very interesting, because there we start imagining kind of different courses of history. And again, this is a mathematically separate rung, because again, there's many situations here, even if we know how they react to interventions, there may be different mechanisms at play that affect how they would behave under counterfactual questions. To really have these three kind of layers. So a typical counterfactual question, right? Like, I don't know, whoop. So I have never smoked, but I wonder if I had, what would have happened, or so on. So keep this picture in mind. There's 3 tiers, and I kind of want to take this and move it into programming. Because probabilistic programming, as we have done it so far, is firmly on rung 1, right? It's a very nice, it's a very expressive framework. We love it, that's why we're here. But it conditions, and conditioning is not intervening. It's really here. So the question is, how can we lift? What even should go here or here? What's the kind of probabilistic programming that is enriched to talk about interventions or counterfactuals? And that's that's by definition what causal probabilistic programming is, but I want to show you how we can start doing it. So what I will do is first give you an outline about kind of Pearl's theory of causality. So this is the maths, this is how to do it by hand. And then I want to get into how to lift this into fully fledged languages. And because this is not solved, this is very open, right? I will talk about what are the goals, but also what are the difficulties, what kind of trade-offs are in there. Some mathematical facts. If you're a theoretician like me, I have lots of stuff, and I have these 2 symbols, right? So we have some insights that are already there, and they are cool, and then we have way more questions. So pay attention to these symbols and talk to me about them, because all of them can spawn off into research. So this is the recap. This is the kind of classic maths part of the story. If you open Pearl's book, and you would say, what do you need to answer these 3 rungs of the ladder is this. If you want to answer observational questions, you just need a Bayesian network. You need random variables, and they have a joint distribution, and you measure, and then you can answer all the statistical questions. If you want to answer rung 2 interventional questions, you need something called a causal Bayesian network. I will explain what that is. And but this is pretty intuitive. And if you want to ask counterfactual questions, then you need something that he calls a structural causal model. That's more specific. I will also explain what this is, but there I'm actually not sure if we need this is actually correct, if this is the right formalism. It is a formalism that works, but Yeah, but again, this is how Pearl would explain the story. Okay, so rung 1 is easy to explain. We just need a joint distribution, and then from the joint distribution we compute. And this is what probabilistic languages do very nicely. We sample, and then we condition or do any kind of inference. And in a Bayesian network, we have a bunch of these variables, and then we draw like a DAG structure on them. We draw arrows between them. But the arrows mean something very specific. So arrows, or absence of arrows, means that there are certain conditional independences that we assume, or that are valid in between this set of variables. So for example, if we draw a diagram like this, right, x to y, but there's a z in the middle, and I don't draw an arrow here, that means that x and y are conditionally independent given z. So if I condition here, then x and y become independent, so whatever influence there is kind of mediated by z. Except, as a Bayesian network, this diagram here is actually equivalent to this diagram, where I flip everything around, because that's the same conditional independence relations, right? It still says x and y are separated once I can condition on z. So this is important to keep in mind. On rung 1, these DAGs just talk about conditional independences. They don't talk about a causal flow of information, because we're on rung 1. It's not causal. If we want to read this causally, we need to go to rung 2, and then it means what you actually think it means, right? So in a causal Bayesian network, it looks the same way. We draw it the same way, but now the interpretation is very different. The interpretation says, here, if I draw a link between variables, there is at least a possible direct causal influence. And then there's kind of these transitive influences, so x can influence y, but only mediated via z. And under this interpretation, this structure here is different from this structure, because here, well, y listens to x, and here x listens to y, and not the other way. So this is very important. But if we just observe distributions that are induced by this, we can't tell the difference. We cannot tell causal structures usually by just projecting out and looking at correlations. But we can distinguish these two once we start doing interventions, right? Once I say, oh, set like z to this value, then if we intervene z to be something, then here y will change. But here y will not change, because y doesn't listen to z. So that's why we need interventions to be able to tell apart causal structures as opposed to just Bayesian networks. But of course, we have this projection that I showed you between the layers. So from every causal Bayesian network, we can just forget about causal influences and just remember statistical influences, and we get a normal Bayesian network. But yeah, if we have this structure and what Pearl calls causal mechanisms, so I write down exactly like how z listens to x and how y listens to z, then I can answer interventional questions with this. How do I do this? Well, there's an operation that takes a causal Bayesian network and performs the intervention by like graphically or whatever. If you think graphically, you cut some links and you just plug in values. So there's this kind of surgical procedure that from M produces a new thing, M with Z intervened. And now here the data flow is cut, so if I intervene, Z doesn't listen to X anymore. And then what Pearl writes, something like P of Y given do Z, is just the distribution that we get under this new post-intervention causal Bayesian network. So this is a notation for causal quantities that we're interested in. And the way to compute them is to create the causal model and then compute it and look what we get there. Of course, the question is sometimes we don't know the model. How can we get to it? But if we have it, then this is the procedure. And importantly, so this do here, this is not a conditional distribution. This is very different from just putting here y given z, which is a rung 1 quantity. So an example from this, here is a very classic situation in empirical sciences. We have some sort of x, like a medicine which affects a treatment, y. But we assume that there's some common cause z here which affects both of these things. then if we just condition y on x, we will not get the causal effect because there's this confounding factor there. For example, smoking and getting cancer and age. So if it was the case that just older people smoke more and they get more cancer, then by conditioning we learn nothing. So what we need to do is somehow compute away the influence to get to the quantity here that we're interested in. And in this case, if we know the distribution, then actually we can find a formula which is called an adjustment. So we compute sort of a joint conditional here with x and z, and then we average over the z's with the frequency that they occur. The formula is not important. The point is there exists a formula with which sometimes we can compute causal quantities from observational ones, but only sometimes, right? And this is what's meant with identifiability. So identifiability means under certain circumstances, a certain causal quantity that I'm interested in, I can compute it in some way from information that is further down the ladder. So in the mathematical sense, this means it descends really as a function. So here my intervention is a function which takes a causal model to a causal model. I can take a causal model and project to just get a distribution. And then sometimes, right, there exists a way that I can go directly from distribution to distribution by doing this. So if a factorization here exists, then we speak of identifiability, but it really might not. So classical situation is if I have just X and Y, smoking and cancer, and there's some sort of hidden factor which confounds everything, and I don't know what that factor is, and I have no assumptions about it, then I'm out of luck. I really, like, if I just know P of X and Y, then I cannot identify P of Y given do X, because there's many different causal structures which are consistent with my observations, but they would predict very different things under interventions. Sometimes though, and this is where stuff gets to be really interesting, if I make more assumptions, so this is very famously, here I have hidden factors that I have no control about, and I have smoking and I have cancer, and there's some sort of intermediate quantity here, so often something like tar in lungs, and the assumption is here that I assume that smoking affects cancer, but the whole influence is entirely mediated by how much tar we find in people's lungs, and this is a quantity we can measure. So now if we can measure the joint distribution of X, T, and Y, but not hidden factors, it actually turns out that the hidden factors don't matter. We can identify this effect by a more complicated formula, which is kind of magical. So this is one very interesting direction to find out when things are identifiable, and Pearl has sort of answered his own question. So he came up with a system called the do calculus, and it's really strange to read as a computer scientist because it seems incredibly informal. Like it manipulates sort of formal expressions where you have some probabilities of variables and then you can write do somewhere, and you have rules for manipulating them that are sometimes like the normal rules of probability. There's algebra, but there's also some graph theoretic assumptions. And then once you're done manipulating expressions, then sometimes the do goes away, and then you've identified the effect because you can compute it. This is the talk that we had earlier. And so Pearl says this is also, so it's sound, but it's also complete in some sense, right? So you can derive something in do calculus if and only if there's really a very strong unconditional notion of identifiability that doesn't assume anything about the model. So this works for any factorization. If you want to assume that there's, I don't know, things are linear, then you can do much more. There's this whole notion of partial identifiability, where even if do calculus says you can't, then sometimes you can still do a bit. But do calculus, if you can derive it, then you have this very strong identifiability statement. So that's cool. So this is something to keep in mind. And then there's this rung 3 stuff, counterfactuals. So then we want to think about hypothetical situations. So there's a real world where I observe some stuff, and then I create this counterfactual world in my mind where there's also random variables, but I want to relate the counterfactual world to the real world. It should not differ, in wildly weird ways. It should kind of have this all else equal. But people argue what this means philosophically, or in our case, we just need to be very precise in kind of specifying what all else equals means. So we need to say which random variables get shared in the counterfactual world and which variables get resampled. So to give you an example, here's some code, so let's go through it. Here I say x is a coin flip, and y is just x, unless an error occurs with some small probability, and then we XOR this here. So y is x unless we flip. Okay? And on this side we have almost the same thing. It also says y is x except when an error occurs, but we have two different errors. We have here the error 1 only matters if x has 1, and the error 2 only matters if x is not true. I think this is strange, because on the level of joint distributions this completely doesn't matter. You don't see if there's 1 or 2 sources of error. We just see how y is almost perfectly correlated with x except for 10%. Those programs even react the same to interventions. If we intervene on x, okay, yeah, y will listen to it. It's the exact same causal structure, but it's a different counterfactual structure. So the amount of sources of error that we have really matters. If I ask you this question, so given that x is 0 and y is 0, what would have happened if we set x to 1? Okay, let's see on this side. If x is 0 and y is 0, then this implies that e must be 0, right? There cannot have been an error, otherwise we would have seen 1. But if there's no error and I set x to 1, then y is 1. Okay, that's easy reasoning. What happens on this side? Okay, if x is 0 and y is 0, that means there cannot have been an error 2, because otherwise we would have seen 1. But now if I set x to 1, then there's this whole different error that we have no control over, so we will see y with 90%. That's weird, right? So we have two programs which are very, very similar, both as joint distributions and as causal Bayesian networks, but they behave different under counterfactual queries. So which is why Perl solves it in this way. Perl says if you want to solve counterfactual queries, you need to be really, really explicit and make everything deterministic and kind of pull out all your randomness into explicit variables and then proceed deterministically. So a structural causal model is this. You have a bunch of independent variables, which are these u's. Think of them as errors, and the errors are independent, and you have priors on them. And then you have a bunch of dependent variables, in this case x and y, and the dependent variables are defined in terms of independent variables and other dependent variables. So for each of them you have a defining equation in terms of deterministic functions. Okay, fine, it's something we can do. I find it very specific that you need this amount of determinism to answer counterfactual queries, but at least it works. So if you write down everything like this, then you can answer counterfactual queries by taking your query, then you manipulate this model, so you can write down what the real world is, what the counterfactual world is, then you figure out all the distributions and kind of press it through. And of course, if you have a structural causal model, you can also project it down to a causal Bayesian model by integrating out all these variables here, and then you get distributions. Okay, that was the math part. This is how this is done on pen and paper, but we want to program, right? We want to have causal probabilistic languages. So what is causal probabilistic programming? It is a probabilistic language which supports causal queries, either interventional or counterfactual. It's as easy as that. Either it supports it or it can kind of reason about it internally. And what's important is we want this to be a general purpose language. We don't want to write a framework for structural causal models. I mean, these things exist, they are fine, but we want to do probabilistic programming, so this should be, I don't know, ideally Turing complete, or at least very, very flexible. And what are the goals of this? Well, first of all, talking about causality is really confusing, like even in normal conversation or on paper or writing it in do calculus. Like it's really a mess. So programming has the advantage that it's very clear and it's very operationalized. So I already hope that we get clarity, we get insight from developing these kind of languages that we want. And we get lots of tools to aid us there. So we get type checking. We get rung checking. What do I mean by this? Just to say the kind of thing you're interested in, on which level of the hierarchy is it? Is it an observational quantity? Is it counterfactual? Is it interventional? This is surprisingly subtle. I looked into a discussion online that discusses heredity. So, you know, these weird statements that always go into the press, like, oh, intelligence is 180% inheritable. And it's not an error that I say 180. These percentages can be above 1. So you're like, what is this weird definition? Part of it is that people don't disagree on which rung this is. If you check it, it looks very much like it's a counterfactual quantity. But then you look into the literature and there's a book arguing, like the whole first section, just saying that, no, it's a rung 1 quantity. It's actually not counterfactual, even you think it is. So this, I find this fascinating, like just having a kind of type theory that tells us where the quantity that we care about lives, eliminates lots of confusion. Then if we don't know causal structures, then often we want to do inference over possible causal structures. So there's a very higher order thing going on here where we would like models, causal models, to be kind of first-class structures in our language. So those are all great goals to have just in terms of clarity. But then, of course, we also want to automate. So we want to write a model once and then kind of do this whole causality workflow automatically without having to like open things up again or do it by hand. And we also want expressivity, right? If we can just write an SCM by hand, okay, then this is easy, but this is often not nice to do. So those are the goals for causal probabilistic programming. And then, how do we actually use these things? What's interesting is that there's kind of 2 different workflows that I've found so far in terms of what we have. The first one of which is we have actually a fully specified causal program. So it's completely runnable, there's no holes in it. This seems restrictive at first, but then remember we're kind of Bayesian, so whenever we don't know something, we can just put a prior there and kind of run it and then learn. And yeah, maybe the advantage of this is that it's immediately runnable, and we don't need to worry about things like identifiability, because we'll just learn something and we'll predict something. Of course, if we do nonsense, if we try to learn an effect that is not identifiable, then the result will be meaningless. So we'd still need to think about it. But at least in terms of the language, we can run it. So then you're in this whole idea of kind of Bayesian analysis of causality, which is maybe not the traditional way of doing it, but it's very compatible with programming, and it's something that has received attention. Or we leave holes in our program, so we admit that some mechanisms are unknown, and then what we really want to solve is a lifting problem, right? We want to ask a query about a program that is like on rung 2 or something, but all we have is a program on rung 1, and we want to add something. We want to add annotations or information or something such that we can answer the question. And to solve the lifting problem, usually we have to do math, so then we get into like rewriting what you guys talked about, or interactive theorem proving. I'll say something about this at the end. I'll mostly be concerned with this though, because this is nice as a language that just runs, and the 2 examples that I'll show there of this form. So let's get started. What's nice is that by virtue of programming, we're actually kind of already causal. It's a program. It's written sequentially, and like variables downstream listen to variables upstream. If you have stuff like reactive programming, this is very clear to you. So actually, in writing down a program, I'm kind of writing a causal program without even thinking about it. To pretend that it's all observational and that I can reorder lines all the time is unintuitive. So it's nice. And then I can actually identify causal Bayesian networks or structural causal models with just very simplistic programs, right? As essentially a list of assignments. So these things that I've shown before. Yeah, okay, that is a structural causal model. I've even written it as a program. So I can say that I have a sort of base case against which everything else needs to compete, and the base case is these very simplistic programs, and then on them I can solve my interventional or counterfactual queries by program transformation. We've seen this also some time, but so there's papers in this vein. Like you come up with some sort of DSL think this one is in Julia, and you do the program transformations, and this is fine as long as you're sitting in this fragment. So here's an example. This was this XY example from earlier, and remember I wanted to say, right, x and y are 0, and I set x to 1. So I have this little workflow where I say I take my program, now I need to twin it, so I need to create the counterfactual world. So everything with a prime here is counterfactual. I introduce this and I introduce a y prime. Then I need to do the intervention, which what it does is it just sets x prime to 1. And then I need to condition on my factual branch, which are usual observed statements. And then this is a probabilistic program that I can run and I'll just get an answer. So this is the basic workflow that I can do if I'm in this base case fragment and I want to do program transformations. But that might not be what we want to do. That might not be sufficient, right? Because the SCM fragment is very limited and we have a full high-order language around it, and I want to write flexible models. So then the question becomes, how can we do this whole thing compositionally? How can we do causal queries in a way that of course, like, we can expose the entire source code and try to mess around with that, but that's never nice and doesn't compose very well. What we want to do is to expose just a tiny amount of extra intention of our program so that we can use it to answer the queries. And to kind of come up with what we need to expose, this is exactly the challenge. And I can't tell you what it is, but I can give you some indications of some things that have been tried and that work more or less. But in the end, the problem comes down to this. We want to intervene at certain points, and we've called them intervention points, and we need to identify locations in programs. This should be a user choice, by the way. Like, if I have a program that does not expose any intervention points, that's completely fine. I just don't want you to like intervene on the internals of my thing. So I need to make a conscious decision. Here is a place you can intervene, and I somehow need to expose this, and then you can use it in your causal workflow. But how exactly do I identify these points? How do I expose them? There's lots of questions. I can do everything statically. It's kind of static analysis thing. This is already not bad. But then the question becomes, can I be more dynamic? Do I want everything to be fully typed, or am I more like just run and see what happens? Then very subtle things like, do I want to allow interventions in interventions or models that can like counterfactualize themselves? Sometimes this runs without problem. I wonder if this is meaningful. But yeah, those are decisions to go into. And then there are these kind of technical approaches to how do we make this work. And I'll show you a few of them just as glimpses. So some of them are just we name everything, or we use algebraic effects, or we use grading. And grading is the one that I've worked most on. So I will say a bit more about this. But so, for a brief overview, so one of the first languages to do this is Omega here by Zena et al., which is a very interesting language. It essentially uses dynamic scoping to do counterfactuals and interventions. So you have a little do operator which you can apply to programs. And it does what you think it does, but then if you think about how it's implemented, it's actually pretty weird, because it will evaluate this expression, but everything is very lazy and very dynamically bound. So all expressions kind of remember the environments under which they were computed. And then you hit y, and now you see, oh, but y should actually be x plus 2. And then you can walk this lazy expression and say, oh, y was assigned here to x plus 1. Ah, no, replace that by x plus 2. So this works, but it needs a complete rewiring of evaluation strategies and so on. And I have no idea how to type this, because like how would you even do that, right? You need to go into expressions and kind of know what was in scope inside of the expression. So it's also a bit strange. Then another language that has been created here is Cairo, which, as I mentioned, sits on top of Pyro and relies heavily on this Python effect system that was created already for Pyro. And it also relies on vectorization in a very deep way to like encode interventions and branchings, and then work I've been doing in this collaboration was kind of to disentangle all these different things that go into one in Cairo, and we have a Haskell port kind of this that makes it a bit clearer what's going on. But in the end, what's the idea? So the idea is to use an effect system to specify essentially what happens to sample statements. So you already know, like here in rung 1 probabilistic programming, if we write sample, it can mean very different things. So in this paper, this is called modes. Sometimes when we see sample, we really want to sample. But sometimes when we see sample, we later want to give evidence, and it should actually just induce a factor statement or something. Or in this case, sometimes if we say sample, what we want to do is create an intervention point and intervene there. And one way to kind of change dynamically the meaning of what sample means in a program is to use effect handlers, because then later we can say handle this by sampling, handle this by factoring, or handle this by intervening. So this has been used in Cairo, but then of course this doesn't solve all the problems, because now your effect system needs to deal with the problem of tracking intervention points. And you have type systems for effects, so there's stuff like row polymorphism. You get pretty far in Coca if you try to do this, but then I looked up somewhere and they say that Coca doesn't have answer type polymorphism, which is where you get stuck. That's all I know about this. Then another thing is also, if you want to be more dynamic, then you need to think of generating instances of effects kind of on the fly. I'd love to understand more about the effect picture and have a type system for it. I mean, so if you want to remember, the question here is, intuitively an intervention point is very similar to a delimited continuation, because you just, at the point where you sample, you remember, oh, here's a point, I can go back later with like different data and then run again. And if you want to type delimited continuations, it's a similar kind of mess. So this is the first thing. I mean, there are type systems for delimited continuations, but do they solve this? Type theoretically, probably. Now, is the semantics correct? We've had disagreements about this, because is an intervention just a delimited continuation? Maybe, but for counterfactuals it gets weird, because you interact with the world and some things should not run again, but then some things should be taken from data you've already computed. But yeah, this is one direction. Then a very nice direction is to use traces or make traces explicitly. This is already something we do on rung 1 probabilistic programming all the time, right? So if you think of your basic MCMC, you have kind of two choices how to generate a proposal. One is to just pick a point in your trace and resample, and then run the entire continuation again to like generate all the choices. If you think about this, so this is an inference algorithm for a rung 1 problem, but it's kind of using an interventional approach. You use causal structure of the program. So this is, this is causal MCMC or something if you want. Then you figure out that this is not very efficient, because you make big steps, you regenerate lots of stuff. So you can improve this by just picking a site and just changing that site and keeping everything else as it was, and then accounting it for it with the factors. But that's counterfactual. That's like the natural direct effect or something they call this, where you say, oh, I keep everything the same and I just change one quantity. So you get these kind of anti-causal or counterfactual traces. I don't know if that's useful to think about, but I mean, it tells us that traces could play a part in causal programming. And I mean, Alex has typed them. And what's also interesting is that if you make a probability monad with explicit traces, then so you guys point out that this is a graded monad, and indeed grading is a very cool idea. So a graded monad is like a monad, but you attach a tiny piece of information that tells you a bit more about your effect, and you track that statically. So you grade in a monoid or something, and then you have a return which says for every x you can make a computation that is graded over nothing. So it's free. But then if you bind computations together, their grades multiply. So the classic example is, instead of using the list where you have any amount of non-deterministic outcomes, you can use the graded list monad, which is graded by natural numbers, and you know exactly you have n outcomes, right? Then the return says you have exactly one outcome, and if you sequence two computations that have one has n and the other one has m outcomes, then you get n times m outcomes because they form the Cartesian product. So this is a classic way of kind of fine-graining effects. For these samplers, we have the same thing. So there you grade over the trace type, which is this record of all the samples that you make. And if you sequence two computations, then their grades union. And for interventions, we can do something very similar. And actually, that's quite simple. So I wanted to put this here. So for interventions, I grade in intervention points, which, to be precise, I grade in just list of types. And this list enumerates all the intervention points that I have in my computation and what their types are. And now what's a monad? So to give an intervenable computation with return type x and intervention points a1 to an is to give this function. Well, it takes all the arguments a1 to an and outputs a distribution over outputs. But instead of taking n inputs, for each input I now have a maybe input. So I can either give it a value, which means I want to intervene there, or I give it none, and that means keep your original data flow. So very, very simple definition. And then here, yeah, indeed, if I have these lists of intervention points, they just concat. Fine. Yeah, that works. I can, if I write this as a program, the way to generate this grading is to have a little primitive function int, which means create an intervention point. So it takes an x and also returns an x, but also creates an intervention point of type x. So it has this funny graded type. And what does it do? Int x, well, if we call it with none, it means just take the original piece of information that was there. But if we call it with some new value, then you take the new value. So very, very simple function, and like here's a program in this graded monadic style. So we sample, I don't know, some hidden factors, and then I sample if the person smokes or not, but I also create an intervention point. So this program will have return type h times s, but it will also have grade s, meaning I can later intervene on the value of whether this person smokes or not. And grades are also cool because there's independently a lot of recent interest in this. So Sam has had a very nice paper with Jack here where grading shows up in imprecise probabilities. So there we have two sources of randomness, kind of probabilistic uncertainty and Knightian uncertainty. And they don't interact well in, like, if you put them on the same footing. But if you put one of these randomnesses into the grading, then it all works out very nicely. And there's also a kind of string diagrammatic way of drawing graded string diagrams, which actually, this is not from the paper, this is stuff that I drew independently, and they are completely the same formalism. So here this weird plus to me means create an intervention point. Data flow goes up, interventions come from the left. So here we have a program that has two variables, and you have two ways of, you can intervene here, right, and you can intervene here. And then there's some equations. For example, if you shuffle data flow around, you also need to shuffle interventions around. And and here to perform the intervention, you draw this as kind of bending the wire, right? So here data flows up, but if you say take instead this value, then you discard this one and you take that one. I don't know if you care about graphical algebra, but if you do, then it's very simple and it's very nice. So I think grading is a very nice idea. It's something that we managed to work out that is nice, because for lots of questions we don't know how to do it, but if we want to do statically determined rung 2 causal probabilistic programming, I would say grading solves it. Now this is restricted, so we can ask, can we make things more dynamic or generative or first class, which grades are not. Grades are static meta things. So this is still open, but at least it does what it does. Now let me see how much time I have. Perfect. a bit of theory to torture you at the end. So I have avoided category theory so far, but of course this is kind of what I think about is we have SEMs, and I really want to get a handle on what they are structurally, and this isn't very known. So one thing that would be nice is to say SEMs take independent variables to dependent variables. So can we make them into a morphism of some kind from independent to dependent? And this seems nice, but then it becomes really weird if you try to do it, because okay, independent variables are fine. They are very clearly in the domain of whatever morphism this is, but dependent variables play a kind of double role where they are outputs, but they are also a bit like inputs. And actually the intervention operation takes here an output and shuffles it to be an input. And yeah, it really has these both roles, which I think category theory doesn't like, or at least I don't know the kind of category theory that accepts this. So I've tried stuff like hypergraph categories. This is things where you can bend wires, like relations, where you can make inputs to outputs. But those things are very symmetric, and this is not symmetric. Interventions are not symmetric. So it doesn't satisfy this. Maybe it's a weird kind of skew hypergraph category. No idea. But hey, we can write it like logic, so we should solve it like logic. I've also tried polycategories, which is a more linear logic-y thing. So there you say we have two different connectives, right? So in linear logic, this would be here tensors and here pars, which it makes sense that we should use different connectives here because, again, input variables and output variables are not symmetric, so they should compose differently. But it's also not a polycategory. So yeah, I don't know what this is. This would be very cool to just give a name to it. But so far, we don't know how to make SEMs into morphisms. We can do the next best thing. We can make SEMs into objects. Just means they are an object of my category, and then I discuss what a morphism of SEMs is. And maybe that's interesting. So it turns out some machine learners have proposed very recently a definition of this. This isn't even SEMs. This is a Rung 2 paper. They say what's a kind of mathematical model of something that reacts to interventions. They call this a causal space, and derive a bunch of stuff. This paper is relatively nasty to read because they just use lots of measure theory that in the end doesn't matter. After a long time, I figured out that if you write this in a category, a causal space is exactly a morphism of this shape. Now, if you squint at it, this is exactly the grading that we used, right? So we have n variables that come out. So it's something that takes n input variables, but for each variable we can say intervene or not. And it also gives n output variables. Now, this accounts that exactly what I said before, right? These variables play a double role. So they kind of show up on the domain and the codomain. And we have different monodal structures, and we have self-grading. So it kind of all ties into the things I've been saying, which I found very nice. And I mean, I much prefer this definition over this. Also, if you like dependent types, so for interventions, we just had to grade here, and we just say +1 everywhere. So this is a non-dependent, I don't know, you can implement this quite easily in any of your favorite languages. If you want to do counterfactuals, it seems to me things get dependent a bit, but they get very, very slightly dependent. So here's a rock definition. This is essentially the maybe type, right? So I say something of type default A either has value default, that is like none, or it has value novel, which is some. But I've also attached just an extra default value to this type that tells you, oh, in case I say default, you actually mean this. This type is isomorphic to maybe, but in a weird sense that is still slightly dependent. So that if you use this, you can write something here that looks a lot like an SEM. So in this definition here, which is a dependently typed function, it has independent variables x and y, and then it says z. Well, z is also like a variable, right? But it has default type x plus y. So if we say nothing to z, it will have value x plus y. But if we want to intervene on it with, I don't know, 52, then it will be 52. And this is a dependent type because, yeah, the type here depends on this expression. So, yeah, I believe that this silly kind of default type theory actually gives us a way to define a category of SCMs where essentially, yeah, we're doing dependent type theory. There's an analogy with automatic differentiation that I really want to understand. I think this is probably something that people know in like a folklore way, but I can't say what the precise formal connection is. So in causality, right, our base truths are these SCMs. They are a class of programs. It's the same thing kind of as an autodiff where we say the base truth is a computational graph, which is also a very kind of simple program. And then we run backprop on it. And backprop, mathematically what it should do is compute the derivative, right? And then, so rung 2 interventions in causality seem to me very similar to computing total derivatives, and rung 3 counterfactuals kind of compute partial derivatives. I don't know, you can glance at this, but we don't have time. I don't know if this is true in any formal sense, but what's nice is that for autodiff we have these nice differentiation macros that extend this to higher order languages. So maybe this is what we're looking for. Like if we understand this analogy, then here can be causal probabilistic programming. Yeah, category theory, okay, Markov categories are nice. We have a paper where we do things in string diagrams, which is great because it's the semantics version of what you guys did with syntax. So that's very nice. And here's the last thing I wanted to show you. So I happened to code up Markov categories in the Unimath, which is a project like homotopy type theory project in the rock proof assistant. And then I had the definition, which was kind of there for fun, and it was like, oh, what can I prove with it now? What's cool? And actually, I can prove identifiability statements. So here, like you can go to my GitHub and just look at this file. But what's the type of statement here? So I define what I call strong conditional identifiability, and it's just a definition like this. So it's the lifting problem, right? I have something on rung 1, and I want to ask, does any choice of lift here compute the same quantity? And then here's this classic example of like, so this is the backdoor adjustment formula. So x affects y except z confounds it. And I want to prove that I can compute the causal effect by adjusting for the confounder. And yeah, so these statements look horrible because this would be much better graphically, but we don't have it. So it's just algebra. So it's ugly. But what's also nice about it is there's no measure theory in it. There's no numbers in it. This is as formal as it gets. Like this is pure algebra. Markov categories are the kind of algebra of composing probabilistic processes. So I can define what my model is. Do you see it? Yeah, so the model just consists of three maps. This is a factorization. Then I say what the joint distribution is of a model. I say what the interventional distribution is of the model. And then I want to show that if I have a certain full support assumption, then from the joint distribution I can identify the interventional distribution. And I have to prove it. And yeah, then there's like, I don't know, 200 lines of shuffling this algebra around. But as a formal statement, I found this really nice because we can just prove it. And this assumes nothing. Like it's a pure Markov category with conditionals, so continuous, discrete, you name it. I think this is a very nice thing that category theory can contribute, is to give very formal proofs of these identifiability things. Is it complete? I don't know. This would be fantastic to show that I can do calculus in rock or something. Yeah, so I hope to have gotten you excited in causal probabilistic programming because it's here and people are interested in it and it's exciting, but there's lots of challenges. Let's work on it. Thanks.
Yeah, thanks for the great talk. It was super interesting and also made the concepts a lot clearer to me. I was wondering about your ROC implementation. You said you used the homotopy theory version of ROC. Yeah. Do you make use of homotopy type theory like features? Okay.
Because my co-author was interested in the homotopy definition of Markov categories, but it does not matter.
Okay, I was just wondering, yeah.
It's just what I
have. Whenever I see A+1, I think, is that A plus bottom? Have you thought about doing any kind of like domain theory here, or thinking about, you know, it seems like in this interventional stuff, it's saying you have different levels of knowledge about your variables, and you're saying, if I forget something about one of the variable, what gets reconstructed? Okay, sounds good.
Thank you. Thank you for the interesting talk. I don't know if this is the right question to ask about, maybe since this is an introduction to the field. Is there there's some sort of expressivity questions you talk about? Is there some sort of problems you have in mind as sort of application fields or like benchmarks where you can say, yes, we can express this sort of stuff using this framework? But of course, just the mathematical connection is sort of interesting by itself. But that's sort of another question that comes to my mind.
If you want to go practical, so from languages that exist, I mean, Cairo is the strongest contender, and on the Cairo website there's a very nice set of kind of progressively harder tutorials. Yeah, have a look there. So this is what we do in our Haskell port, is to see, now the simplest class of problems we can replicate it, but then suddenly, this uses a weirder kind of, especially with counterfactuals, you can get very weird because you can like plug in arbitrary expressions or create new variables. So it's kind of, we start out with a very simple model and we see how far we get, and then suddenly it's not expressive enough to do this application. And then we're like, should we modify it? Is it worth the pain? But then maybe yes. Those are the right kind of questions to be asking. I think for this, look at the tutorials, look at the kind of things people want to do, and then see if you can do it.
Cool. As a follow-up, so then the sort of language design perspective is that you're trying to give more grounding to the sort of stuff that happens in Cairo and sort of make it safer. Is there sort of from that perspective? Are you looking from that perspective, or sort of just giving more mathematical foundations to what's happening?
No, there's different avenues, and I try to do several of them. I mean, I'm a very mathematical person. Like, I like the theory, but I also like understanding Cairo. Those are separate projects. But then maybe if we find a good answer in one, then it might inform what we want to do in the other. But I mean, you have now you have all these people trying to do counterfactuals with LLMs. So what goes in there? You have Python code or some sort of library that computes something, and then they rewrite everything as SCMs and do it by hand. You shouldn't do that. You should have a language where you take the existing code and it's capable of, like, I mean, the way autodiff works. I think autodiff is a really nice. You don't want to go through your code and compute derivatives by hand. There should be some sort of formalism that takes what's written and then lets you answer these questions.
Yeah, I think that's a good comparison. Great, thank you very much.
Okay, maybe we should move on to the next talk today. Speaker is Daniel Zilkin, and the topic is verifying sampling algorithms by distributional invariance.
Thank you for the introduction. Yes, in my talk we will verify sampling algorithms by using distributional invariance. So probabilistic program verification in general means for a specified precondition to verify a certain post-condition. And we investigate how useful it is to really treat distributions as the main objects of interest, so as a
and post-condition, we really take sets of distributions over the program states. Okay, it turned out our approach works particularly well to verify sampler algorithms, and our running example will be the so-called fast dice roller program. And for the fast dice roller program, we want to verify that when we start the program on any input distribution where n is greater than 0, then on the output, the variable c is uniformly distributed between 0 and n minus 1. So in the end, our goal is to prove this Hoare triple. And yeah, here is the program, the fast dice roller program, introduced by Lombroso in 2013. So it uses a single coin flip inside the loop body, and it computes the uniform distribution for any input n. We can also translate this program into its underlying Markov chain. This is only a part of the Markov chain, namely only the part for the fixed input n equals 3. In general, the Markov chain has an infinite is an infinite object and has an infinite amount of parts for each n as input. And yeah, we want to verify the fast dice roller using distributional invariants. What are those? We define distributional invariant as over approximations of the reachable distributions. Now, what are the reachable distributions? Here we got inspired by some work in Markov chains. Namely, here we can define the reachable distributions as the unique stream of distributions that are reachable from some initial distribution. For example, if we take our Markov chain for the fast dice roller, the first reachable distribution would be simply the initial state. Then we can apply the transitions of the Markov chain once, and we obtain another reachable distribution. And we can continue this stream forever and obtain a whole set of reachable distributions. Inspired by this notion, we defined reachable distributions directly on program level. So for probabilistic programs, how can we define the reachable distributions here? We take a snapshot of the denotational semantics after each loop iteration. So I hope you're familiar with the denotational semantics. This is basically computing the resulting distribution in a probabilistic program from some initial distribution. And yes, if we have this specific setting which applies to the fast dice roller where we have a single loop with a loop-free body, we can now take a look at the distribution with which we enter the loop. This would be now, in our example, the Dirac distribution where v is 1, c is 0, and n is 3. And then we can perform one loop iteration, and we obtain another reachable distribution. So you see this corresponds very well to the Markov chain. We simply collect all the distributions that we reach after a finite amount of loop iterations in one set. And this yields the set of reachable distributions. And now, as I already said in the beginning, distributional invariants are simply over approximations of these sets. Then there's another notion of inductivity. So our invariants, both for Markov chains and for loops, are called inductive if applying the transitions from the Markov chain for an arbitrary distribution from the invariant yields a distribution in the invariant again. And this is similar on program level. Here I is inductive if executing one guarded loop iteration from a distribution in I yields a distribution in I again. And now one of our contributions was to prove a theorem that really an invariant I is an inductive distributional invariant with respect to a probabilistic loop if and only if it is also an inductive distributional invariant with respect to the underlying Markov chain. So these two notions of distributional invariants really coincide, and we combine the world of Markov chains and loops with this. Okay, back to the fast dice roller. Here we found a very specific, a concrete invariant to verify the fast dice roller. So this is a set of distributions, and this might look a bit complicated, but these distributions have to fulfill 4 conditions, A to D. And here, A, B, and C are basically reachability conditions. So they tell us only the states that you can also see in the Markov chain are reachable. Then we have this condition D, which is really at the heart of the fast size roller, because this basically expresses that the variable C is at all times uniformly distributed over 0 up to V minus 1. So this is kind of the most important condition, because then on termination we can conclude that V is greater or equal to N, but C is smaller than N, and then we can really have that C is uniformly distributed in the right interval. But how do we do this formally? The last step, we apply a proof rule for probabilistic loops. So if we have found a distributional invariant, we can verify a loop with it by applying one of those rules for loops. So we have 2 rules, one for partial correctness and one for total correctness. So while the rule for partial correctness tells us nothing about termination, with the rule for total correctness requires an additional proof of almost sure termination of the loops, which we also have in our notes, both for the fast size roller and the fast loaded dice roller. And for the fast size roller in particular, it is the case that this post condition that we obtain, by the way, the closure of a set of distributions is simply the set itself extended by the limiting distributions. So if we take ascending chains of distributions, we add the limiting distributions to it. And for the fast size roller and our invariant that we found, it holds that the closure exactly contains all the distributions where C is uniformly distributed between 0 and n minus 1. And by this we obtain our desired Hall triple, which was our initial goal for the fast size roller. Okay, this already brings me to the conclusion. So we saw a definition of distributional invariants. They are over approximations of the reachable distributions, and the 2 notions for Markov chains and for probabilistic loops basically coincide. Then we found out that this framework is particularly well suited to verify sampling algorithms, and as examples in our work we verify the fast dice roller and also the fast loaded dice roller, which is an extended variant which can not only compute uniform distributions but arbitrary discrete distributions. Okay, thank you for your attention.
Thanks, Daniel. Any questions?
How do you generate those distributional invariants? Do you use some like Markov chain-based methods?
No, you have to really find them by hand. So this is not automated yet. Exactly.
Is there some calculus to do that?
That's a good question. That would be something for our next research, but in general, not, no.
Okay, I think we should move on because we're already a bit behind. But thank you very much, Daniel.
Okay.
From MIT, talking about
One time.
All right. Here's a. Oh, true tone off. Okay. Yeah. Display. True tone. Where is true tone? Oh, true tone. True tone. Oh, is it on there? No.
I think it's in the up here.
Up there.
Yeah.
Display. And then you click on display, and then true tone.
Amazing. Yeah. Okay.
Cool.
Okay. Great. All right. So, hi everyone. I'm Maddie Bowers, and today I'm going to be talking about some recent work on leveraging probabilistic programs to help speed up the synthesis of deterministic programs. So the kinds of programs we're going to be thinking about come from the study of concept induction, which is the ability to learn a new concept from just a few examples. So this is studied both in AI and cognitive science. So in AI, for example, the abstraction reasoning corpus, or ARC, is a popular benchmark where the goal is to figure out the transformation that maps one of these input grids to an output grid. And over in cognitive science, there have been many instances of studying this, including these tasks, for example, where you're given an input list of numbers, and the goal is to figure out the rules that are bringing those input lists to output lists. So the rules might be something like this. And if we're equipped with a grammar over the space of programs, then we can write down solutions to these tasks as programs. For example, this is one that indexes into the input list and then, it indexes into the input list specifically at the position given by the head element. And this second one doubles all of the odd numbers in the list. And so in general, our goal in synthesis is to find short programs that explain what's going on here. And we can formalize this as Bayesian program synthesis. So Bayesian program synthesis formalizes concept induction as a posterior inference problem with a generative model that looks like this. So we have our programs drawn by some broad prior on programs like a PCFG. And after generating a program, we then execute it on our input-output examples, or rather on our input examples, and that's how we produce the corresponding outputs. And so the actual problem here is we're given some input-output examples, and our goal is to navigate this space of programs to find the actual high posterior ones. And in particular, this likelihood we have is extremely sparse. So it's only going to be non-zero for programs that agree with all of the input-output examples, right? That produce all of the correct outputs, that is. And so this is a tricky problem, but a classic approach to starting to tackle it is framing it as MCMC. So in particular, there's a subtree resampling approach people use with programs quite often, where at each step, you're going to take your hypothesis, pick a random subtree in it, and resample a new one from the prior. And so this gives us some way of navigating the space. But for nearly every program in our hypothesis space, we have likelihood 0. So MCMC doesn't really get any help from this likelihood for figuring out if it's on the right track. And a common approach in prior work is to basically come up with a kind of ad hoc smoothed likelihood function that is going to put a bit more mass on programs that produce outputs that are similar by some, ad hoc type specific distance metric, similar to the actual outputs. And so it's about changing the weights on, or the probabilities on these existing programs. And in contrast, that can be useful, but relies a lot on developing the specific distance metric and how well that distance metric actually guides us towards these solutions. And in this work, we're going to take a different approach. We're going to extend the hypothesis space to include probabilistic programs in addition to deterministic ones. So we aren't reweighting any of the deterministic ones. We're just adding these probabilistic programs that can naturally have probabilities between 0 and 1 because they can have some probability of producing the output. And the goal is that these are going to make our space a bit more well-connected and help us on our way to finding these deterministic programs. And so what do we mean by extending the space with these probabilistic programs? Well, if we just take our grammar from before and we add some random primitives to it, then given some input-output examples and any hypothesized programs, we can go ahead and evaluate likelihoods evaluate the likelihoods that those programs produce those outputs when run on those inputs. And these three programs in the middle, for example, all involve a singleton list of some kind. And so they all end up producing, with random contents that all ends up ascribing different non-zero likelihoods to these, or to the input-output examples. Now, the idea is that we can run our MCMC algorithm in a space that includes all these probabilistic programs. And instead of something like an ad hoc edit distance-based likelihood, we'll just use this exact same generative model that we had before. So, yeah, except that now, when we actually evaluate a program, the likelihood is not necessarily between 0 and 1 because these are probabilistic programs. And like before, MCMC is going to do this process of repeatedly resampling subtrees and accepting or rejecting proposals. But one thing to note is that in order to compute the acceptance probabilities for our Metropolis-Hastings ratios, we're going to need to compute the likelihood. And that is, we're going to need to compute the probability that these programs produce the particular outputs we observed. And this itself is a hard inference problem because it involves reasoning over the deterministic logic within the program as well as the probabilistic parts, and these are recursive, sometimes higher order functions. And this challenge actually motivated the development of a language called Pluck that we presented this summer at PLDI for tackling specifically this kind of exact marginal inference problem efficiently. And this algorithm uses lazy knowledge compilation, which is a new approach to solving problems for these kinds of discrete probabilistic programs. So what does this actually buy us? Well, we find that in practice, it gives us a huge boost. So here's a graph with the y-axis being the average number of tasks solved in a data set of these list manipulation problems. and the x-axis is the number of steps of MCMC. And here is that naive deterministic 0 or 1 baseline, and the green line, the green one is the smoothed likelihood with an edit distance, and our method with probabilistic programs outperforms these two pretty considerably. And okay, but what do these trajectories actually look like? Why is this succeeding? Well, when we dig in, we find that the trajectories often involve a lot of wandering around with like a few key moments of big breakthroughs. So for example, here's a task where the solution is a function that increments odd numbers and decrements evens. And we might start with a very general hypothesis like, oh, it's some random list of numbers, which after wandering around a bit, there's a breakthrough of kind of refining this to, say, a map over the input list that generates random numbers for each element. So this is going to give much higher likelihood to our examples because samples from this are always getting the correct length. And so on, there's this process of, at each point, replacing some probabilistic part of the program with a chunk of more deterministic code. And so we're really interested, after seeing this, on if some insights from here could give us a new algorithm that solves this more efficiently. Because MCMC here is spending kind of a lot of time wandering around the space of like kind of semantically equivalent things. And it'd be nice to just kind of like jump through these steps. And so I don't have time to go into much detail on this, but we developed an SMC algorithm based on this idea of refining probabilistic primitives to bring in a bit more deterministic structure. So we've got, just to sketch it out, a population of particles. And at each step, we run a proposal that takes one of these and transforms it. In particular, the procedure is given a hypothesis. We choose one of the random primitives and sample a replacement for it. We then can score our hypotheses with the same likelihood function as before, and finally resample to and continue in the normal way with SMC. And indeed, this does end up helping quite a bit. Makes the whole thing around 6 times faster on those benchmarks. And there's lots more details that I'd love to discuss offline. But yeah, thank you so much.
Maybe the next speaker can come.
Thank you for the great talk. Did you ever notice like garden pathing phenomena in your trajectory refinements? Like, did you ever get like the chain gets stuck at the wrong part of the space because it introduced randomness at the wrong part, and now it has to make a huge edit to like undo that?
Yeah. So that's a really interesting question. Right. Ultimately, these. Okay, I see, yeah. Right, that can happen, especially because, right, ultimately the likelihood here is a heuristic. We aren't magically solving the whole search problem. And so, right, it's definitely possible to like kind of greedily go down one path and then learn that, that you sort of need to backtrack or do something else. And this is why we have the sort of like array of particles. We do have some thoughts on theory for where this will would be optimal, or just sort of more theoretical justifications for this as an approximation of something that's optimal, which I'd be very down to chat about after this. Yeah, thanks.
Thank you.
About sample for well-type functions. This is the true term.
It's something that's been confusing before is that it's sort of located on the other side of the screen than you would think.
Huh. No.
So that if you drag it this way, it
I see.
comes up the bottom of the screen.
Okay, I got it. Thank you.
And then, yeah, do you want it full screen, or is there a...
Sure, yeah, I'll do the
cool.
screen. Thanks, Alex.
So word sampler for well-type.
Oh, wonderful. Okay.
Please go ahead.
Thank you. Bonjour. Welcome. Hello. Considering the venue where we're gathered, I thought it fitting to start with a prayer written by a 13th century theologian and one of the foremost scholars of natural science by the name of Thomas Aquinas. It was written as in order to help his fellow novitiates in the Dominican order to better understand the world around them, the innate beauty of the world around them, and in so doing, to come to a better appreciation of the mind of God. And so I share it with you in hopes that he may intercede for us in our own studies in computer science. In the name of the Father, and the Son, and the Holy Spirit. Amen. Ineffable Creator, who from the treasures of your wisdom designated 3 hierarchies of angels and set them in an astonishing order over the highest heaven, and with exquisite refinement distributed the parts of the universe. You, I say, who are called the true font of light and of wisdom, and supereminent origin besides, deign to pour out upon the darkness of my mind the bright beam of your clarity, removing me from the twofold darkness in which I was born, that is to say, sin and ignorance. You, who make the tongues of infants eloquent, instruct my tongue, and pour forth in my lips the grace of your blessing. Grant me in understanding sharpness, in retention capacity, in learning the right mode with facility, in interpreting penetration, in speaking abundant grace. Inform my start, direct my progress, complete my finish, you who are true God and true man, who live and reign, world without end. Amen. Father, Son, Holy Spirit. Amen. And today, as mentioned, I will tell you a little bit about a word sampler for well-type functions, where our goal here is to try to understand this correspondence a little. Night mode. Huh. How does that work? I can, oh, let me try that.
There.
Oh, okay. Yeah. Perfect. Thank you. Thank you. So there's been some work on trying to embed type theories into formal languages. And there's this sort of elegant correspondence. But what we'd like to do, it's just sort of harder, is to embed a type theory into a formal language, a context-free grammar specifically. And specific, just make it concrete. For any well-typed term, we want a corresponding word, and for every word that should be well-typed. So it's kind of bidirectional. So the picture I like to think about is the following. So we have, say, all possible words of your alphabet, which is sigma star. And what we want is sort of syntactically valid things, but not just syntactically valid. We'd like something a little bit stronger. So LLMs, they can kind of sample from all possible words, but you can sort of constrain them. And so to do that, you kind of just delete the things that are outside the syntactically valid region. This is guidance. But you know, and in the limit, what we'd like to do is just really get halting problems. So we know that's, you know, impossible. But the edge, because the edges of this is just, you need a very high order polynomial to approximate that. So, but you'd like to try to get closer somehow. And so there's a sort of a Goldilocks zone, which is the well-typed things. And that is sort of tractable. So what we'd like to do is sort of sample things from that region. And that's what we're going to try to do. The picture you can sort of think about is like this. The question you should be asking is, well, how can we do this? You know, this is an infinite set. What we can do is we can sort of stratify it. We can take samples, finite slices of this, this paraboloid, and that will give us concentric regions, and we can exactly sample from the well-typed things in each set. So we're going to set a parameter, a parameter that we care about that is related to the complexity of the language, say the length. Length is a simple thing. So we can do that, and we can slice that, and then and it's finite, so we can compute the normalizing constant. We can sample from it uniformly, and that's what we're going to try to do anyway. This is by no means sort of a formal thing, just kind of not too rigorous, but we're going to embed this by assuming a finite type universe and an ambient global context. So what this means is you're embedding a function inside of some, picture an IDE, and it has some other functions it can call, some types, and so forth. And we're going to decorate non-terminals in our grammar with this little annotation, but it will be a vanilla context-free grammar, just sort of as a name that we're going to call it by. And then, so each typing judgment in our type system will sort of get compiled down into the vanilla grammar using a transformer that takes the terminals, the alphabet, a set of types, and generates from that a set of non-terminals that each left-hand side non-terminal will generate. There'll be names for things that we can just simple variables, and those will be, there are unit rules in the grammar. And then functions, which have a type signature that we'll have to respect. And so those are kind of the three main ingredients. We can go into the kind of nitty-gritty, or we can take the sort of a bare syntax that doesn't have this. This would be our like BNF syntax. And then we sort of say, well, we'd like to generate functions inside of like an IDE, for example. And so we can assume like it may have Booleans, naturals, and conditionals, function invocation, recursion. Those are the main three things. We just sort of simplify it. It's a toy language, but it gives the idea. So our expression fragment here, this is just the statements without reference to the surrounding our function signature. We'll kind of follow these static semantics. And we'll say we'll have infix operators just for fun. And so I don't really want to go into the exact, all the details here, but it's a question of just enumeration and exhaustion. So you just kind of enumerate all possible combinatorial choices of your type signature. So let's say you want to generate a function with up to 3 parameters and finite types. So that's a finite set of possibilities. And so you can do that. You just have to, recursion is a little tricky, but you just have to make sure you match the types to the arguments. And so that's, this will help you to kind of give you a rough idea. And then there's a few rules here. We're going to normalize this all down to Chomsky normal form, and that will ensure that each production is binary right-hand side or a unit right-hand side. And so how do we do this intersection with the finite slices? There's a nice reason to do this inside of formal language theory, because context-free languages are closed under intersection with regular languages. And even better, if it's a finite regular language,
then there's very efficient construction for the intersection. So the meta theory is sort of well behaved in the formal language setting. So we can sort of deal with intersections much more nicely. But the intuition is that if you have an acyclic automata, and you want to check whether a pair of non-terminals is parsed by a pair of states is parsed by a non-terminal, then essentially you say, well, either it's a direct step, or there's a midpoint, which is parsed by something on the left, something on the right in the Chomsky normal form, and that's the Bar-Hillel construction. It can be sort of refined using this efficient matrix exponentiation technique, but that allows us very quickly multiply lower onto a GPU, exponentiate it, and then derive the exact regular expression for the intersection. So we just have a toy example here of a Levenshtein automata. Here we have just a balanced bracket type scenario. And this will recognize all and only strings within a certain Levenshtein distance from that original string. And this is our initial parse state, our final parse state. Then you can decode from this a regular expression, a star-free regular expression from the parse chart. And in decoding, there are two ways to do it. One is uniform sampling, where you just assign a bijection to the integers and then decode it. The second is autoregressive decoding, where you have, say, a language model. And you can step through the states of this to extract probable sequences from this finite set. So we have some benchmarks. We kind of run this on a single core CPU, and then do the extraction. Can do something like on the order of 22 million tokens per second from just decoding. This is with the uniform sampler. So there's different ways you can look at this, but roughly it's a kind of a way to do program synthesis and repair in a IDE. So that's our goal. And there's a little tool online you can try at this URL. Open to suggestions on different kinds of type theories that you'd like to try out, and there's some connection to other related work in this vein. Other than that, I'd like to give a special thanks to these people, in particular Ori Roth, who presented an interesting work at PLDI, I think in 2019. He's talking about embedding grammars into type systems. And I got to thinking, well, maybe you could do this the reverse direction. And so that's kind of how I got to thinking about that direction. So that's it. Thank you.
Once you've done the transform into the grammar, how big are the terms in the sort of type annotated language versus just the typical language? And is it a constant factor, or is it an exponential, or like a larger than constant factor blow up?
So this is a good question. There's an analysis of the worst case blow up in the paper, but there we provide an upper bound. Empirically, for the toy grammar we showed, pre-normalization, it's a few hundred kilobytes. Post-normalization would be for these sizes here. You're looking at something like a few megabytes to represent the Chomsky normal form grammar, and then. You can look at different ways to normalize that will reduce this cost, but it becomes formidable when you start to consider large type signatures. So if things that are larger than 6 or 7 in the arity of the function, and it depends also on the finite type universe, how many types you fit into that, as well as the ambient context. Less sensitive to that, but if you have a large API, then that can also add to the cost of the
the meta program, the generated grammar. So we're looking at different ways to reduce the descriptive complexity of that representation, but it's something we're aware of. Thanks. Good question.
Okay, let's thank the speaker. We'll meet back here at 2 p.m.
Okay. Yes, it works.
Welcome back. So for our first talk of the session, we have Gabriella Vanoni speaking about compiling higher order programs to Bayesian networks.
Okay, thank you very much. So this is joint work with Claire de Fajan, who works with me at IRIF in Paris. So I will start just going back to POPL 2 years ago, where we published a work about Bayesian networks. In that paper, we had this kind of language. We had a first-order term calculus, and then we refined it also to a higher-order one, but in the talk of today, I will stick to the first-order fragment. This is a simple first-order programming language, declarative programming language in a lambda calculus syntax. Of course, there are no lambdas because we are first order. We have probabilistic primitives in the form of a sample from a probabilistic distribution D and of a case construct that we use to encode conditional probability tables, such as the ones that we find in Bayesian networks. And finally, we also have an OBS construct that allows us to observe evidence. Values are the traditional values of the call by value lambda calculus, and types, for simplicity, are just booleans or tuples of booleans. So what we proved there was that if a lambda term is typable with one of these ground types, then there exists a Bayesian network such that the semantics of the Bayesian network, so the probability distribution defined by the Bayesian network, is exactly the same of the semantics defined by the lambda term. And there exists also the converse statement, but this is almost trivial because it's almost obvious how to encode Bayesian networks inside this fragment. The point is that from every program in this fragment we can extract Bayesian networks, or at least here we show that it exists. So now the problem could be, how do we effectively extract this Bayesian network from the probabilistic program written in this language? Well, actually, since we proved this result, actually during the proof we also have given a way to extract the Bayesian network, and this is the intuition. Well, this is a probabilistic term, and this is the type derivation of the probabilistic term, but this has been augmented. It has more information with respect to the type derivation with the types that I have already described. In fact, here types are not just booleans, but they are annotated booleans. So here we already add to the types the information about the random variables which are actually defined by our program. And so with this type derivation augmented with the information about the names of the random variables, well, then it's possible to retrieve the Bayesian network just by following a sort of information flow graph. So following the occurrences of the types, of the names, it is possible to derive a graph, and then we could prove that this graph is actually directed as a cyclic graph, and so actually this graph is the Bayesian network defined by the underlying term. But now the point is, we would like to do this construction without considering the named booleans. So just by having here a boolean b and not a boolean with a name, with the name of the random variables. And this will be particularly important when we will go into the higher order realm, when there are copies of subterms, and so we don't know at compile time how many random variables will be present. So we need something which can act dynamically somehow. And this is why we have resorted, in order to build this Bayesian network out of the term, to an abstract machine. An abstract machine, in particular, in the style of Crevin's abstract machine. So I will show you the basic rules of this machine. They are a bit simplified with respect to the real implementation, in order to keep the presentation more easy to follow. Well, when we encounter a let constructor, well, we just record in a data structure called the environment the fact that we have encountered a regex. And so we just record the argument of this variable x, and then we proceed to t. Nothing happens at the level of the probabilistic evaluation, and so this is standard for abstract machines in general. And it is standard as well when we encounter a variable. Well, we just jump to the argument, which was saved inside the environment. Now, this is the first interesting rule. When we encounter a tuple, actually, our machine is a parallel machine. It has multiple threads, and this is why here it's written this tau union, because actually we are executing a set of threads, and we select at each time just one thread to evaluate. But the machine is morally parallel. And so when we encounter a tuple, what we do is that actually we spawn two different threads, one for the argument, which is the left-hand side, and one for the right-hand side of the tuple. So here is when we actually create the parallelism. And this is because in a Bayesian network, if we start from the conclusion, well, maybe a variable depends on a random variable depends on two random variables, and so we have to evaluate the two different branches in parallel. Then, when we encounter a case constant, well, a case constant, this means that this creates a new variable, and so this is why we actually update in our graph data structure that we are always carrying with our state. This is a global graph data structure. We update the set of vertices, adding this new vertex, and this new vertex is named with a new name, and actually we use as name this macro cpos, which is just a macro for saying, well, the name of this node is the tuple term context, so it's the position inside of the term. And then we should add also an edge to the set of edges, and well, this edge is from the last variable that we encountered, that here it's written as p, and we carry it together with our state, and actually this new node that we are adding. And so this is why we are adding the edge p to our current position. And finally, the sample. Well, the sample is exactly the same, so we are encountering a new random variable which has been introduced by the sample construct, but then we don't have to proceed, so the thread just dies, and we add, of course, again the new random variable and the edge, the corresponding edge. So this is our implementation, or better, a simplification of our implementation. And of course, we need to prove also the correctness of this implementation. So what we say is that if we start from the initial state, well, we reach a final state where there are no more threads, and as the graph, we obtain that, well, the graph which has the same semantics of the term that we are evaluating. Of course, in order to prove the correctness of this compilation, we need to prove the confluence of the machine, because the machine is parallel, and so we need to be sure that this parallelism is harmless. Well, why are we interested in compiling lambda terms to Bayesian networks? I mean, why the target of our compilation is Bayesian networks? Well, maybe because Bayesian networks are very interesting and we are fine with this answer. But there is also another possible answer. Well, actually, it is possible to use quantum technology to fasten the inference on Bayesian networks by a quadratic speedup. And this is well known, at least since 10 years. And in particular, in order to exploit this result, we need to translate Bayesian networks into quantum circuits. And so, of course, if we want to do inference on a program and then to exploit this quantum speedup, well, first we have to translate to Bayesian networks. And so what's the point? The point is that a Bayesian network is a directed acyclic graph, and a quantum circuit is a directed acyclic graph as well. And so the translation is actually quite simple, almost direct, I would say. The topology remains the same. And so, well, we can also exploit these the technology of Bayesian networks to make this compilation more efficient, in the sense that, of course, we need the one quantum bit for each node of the network. Networks have maybe hundreds of variables, and so using technology from Bayesian networks, such as pruning, so we can reduce the number of bits needed by just considering the part of the network that we are interested in. Or using conditional independence, well, we can split the network into different networks, and so reducing the maximum number of used qubits. And so this is it. Just for future work, well, we are going to use also higher order programming languages and to cover PCF or call by push value, and to implement then the full stack from a probabilistic programming language to quantum circuits and evaluate it on benchmarks. Thank you.
Thanks very much. So we have time for a question or so while the next person sets up. If they could come forward, please. Questions? Yeah, you go.
What's stopping you going higher order now? Because the abstract machine is already, you have everything you need to.
No, well, yeah, we have started with the first order case, and then, I mean, the abstract machine has not everything we need. I mean, to go higher order is, I mean, we think we know how to do that, but at the same time, it's not exactly trivial. Yeah, because the point is the copy mechanism of higher order computation. So, I mean, at runtime, you will have random variables which are not identified anymore by the position inside the term, but we have to copy, let's say, linear logic boxes. And so, I mean, you need to devise a more complicated way to do that. And also, if the evaluation order becomes really tricky, in the sense that when you are first order, every evaluation order is the same, roughly, because you're linear. But then it's more difficult to deal with a call by value or call by name or call by push value. So, yeah.
Yeah. Thanks. Well, thanks. Let's thank the speaker again. Okay, so next up we have Hussein Mansour talking about contextual distances in randomized programming. As soon as we get the microphone on.
Good. So, hello everyone. So, it's a work joint with Raphael Kribile, and it's about the contextual distances in between programs in higher order randomized programming. So, we consider the notion of contextual equivalence between programs. Two programs M and N are going to be equivalent if and only for any context C. We can get the same observation on C of M and C of N. So context model the environments. They are programs in the same language, and each context contains the occurrence of a whole. And when we put a program M in a whole of a context C, we get a program C of M, and the observation is what we can observe from the execution. Here we are in the probabilistic case, and so we can observe the probability of termination with the value 1. So it will be interesting now not only to say that two programs are equivalent or not, but to say that two programs behave in a similar way with a high probability. Here, for example, I have the program M, which return 1 with probability 1, and the program N, which return 0 with probability epsilon, and 1 with probability 1 minus epsilon. So here, M and N are not contextually equivalent because I can find a context that separates them. So it will be interesting to say that for a very small epsilon, the two programs M and N are very close. And so the question is how we can generalize the notion of contextual equivalence in order to compare quantitatively two programs M and N. So a direct generalization of this notion of equivalence, we have the notion of contextual distances, which is defined as the supremum over all contexts for the difference between the observations when we put M in the context. But here we have a problem which appear this is what we call the trivialization phenomena. The idea is that these two programs, previously said very close, are with distance 1, and it's because we can construct a family of contexts. For the first instance, we construct C2 that takes 2 copies of the program and evaluate each copy independently and return 1 if all instances return 1 and 0 otherwise. And so here, when I put M in the context C2, I will have probability 1 for the first program, but for the second program, 1 minus epsilon to the power 2. From each instance, I have 1 minus epsilon. And so if we increase the number of copies, and do the same algorithm, so when N becomes more and more bigger, the probability for the second program becomes more and more smaller. And so the distance between M and N will be equal to 1. So this trivialization phenomenon was formalized by Kribele and Delago in this theorem. So if we have a probabilistic language in which in which all programs terminates with probability 1 and the context can copy the arguments, so for any pair of programs M and N, either I have M and N are contextually equivalent and the distance between them is equal to 0, or the two programs are not contextually equivalent and the distance between them equal to 1. So an example of a such language, I have T plus, a probabilistic extension of the Gödel system T with the addition of an operator choice here. This negative result of trivialization is not a blocking result. That means that there is another approach to define contextual distances for which we don't have the trivialization phenomena. For example, we can restrict the number of copies that context can make and define the linear distance, which is defined as the supremum over all linear contexts that use the argument exactly 1 times for the difference between the observations. We can also define a family of a graded distance in which for each N, we define the distance as the supremum over the context that copy the argument at most N times for the same difference between observations. Here we don't have the trivialization phenomena, but the trivialization phenomena appear in the limit because the family of a graded distance converges to the trivial metric. And another approach is to work on the first condition on the language and to introduce a divergence programs in the context, such as the amortized distance defined by Thomas Erard. And so here in this work, we provide a new proof of the trivialization phenomena based on a purely probabilistic reasoning. So the original proof of the trivialization by Kribele and Delago used techniques from real analysis such as the Brainstem polynomials. But here we show that a result from probability theory, the law of large numbers, is in the heart of the trivialization phenomena. And so as consequences, we can use results that refine the law of large numbers, such as the central limit theorem, which studies the speed of convergence of the law of large numbers, to study the speed of convergence of the graded of the family of graded distances to the trivial metric, for example. And we can use another results from the law of large numbers and inequalities to find a lower bounds on the other contextual distances. So I will show briefly how we can use the law of large numbers. So if I consider a Boolean program M, which return 1 with probability 1, and so I can look to the program M as a probability distribution, and I can associate a random variable of law Bernoulli P, which return 1 with probability P, and so here again I use the same idea. I construct a family of contexts that copy the arguments k times, and I compute the empirical mean of the distribution. So we have k copies of the program, so we have k independent and identically distributed random variables associated to each copy of the program, and we test if this empirical mean belongs to an interval. So until now it's an arbitrary interval. And in observation, when we put a program M in this context, we will obtain the probability of termination in 1 equal to the probability of the empirical mean belong to the interval. And so here, the importance of the law of large numbers. The law of large numbers state that the empirical mean of a distribution converges to the expected value of the distribution. And so here, if we have the expected value of the program belong to the interval, we will obtain probability 1. And if the expected value is outside the interval, we will obtain probability 0. And so for two programs, M and N, here we have a graphical illustration. If we consider a program M with expected value P and program N with expected value Q, different expected values, so here M and N are not contextually equivalent. And so if I choose the interval around the expected value of the first program and the expected value, and in a way such that the expected value of the second program is outside the interval, so if I increase the number of copies here, so from an order k, I will obtain the probability of empirical mean in the interval for the first program will be equal to 1, but for the second program it will be equal to 0. And this is for the Boolean case, but you can switch easily to the general case using the if-then-else constructions. So for the future works, so we have a few inequalities that come from the law of large numbers. So we have a few lower bounds that we can find for the other distances, and so it will be important to compare the lower bounds in order to define which is the best lower bound on the distance. And we have also the idea to construct a new connection between theories, between the trivialization phenomena and the threshold function theory. And again, we have inequalities that come from threshold function theory that we can use to derive lower bounds. And that's it. Thank you.
Thanks. Are there any questions? Time for one or two.
Thanks. Yeah, so you said something about introducing divergence breaks the trivialization result.
When we introduce the divergence, okay, in a language that include divergence, we don't have the trivialization phenomena, but you will mean the distance, the amortized distance, or in a general language?
Why don't you have? Yeah, why not?
When you have divergence. When we have divergence, so for example, if I construct the context and with an operator choice, okay, with a divergence, with a choice between the divergence and the argument. So in each time I will use the argument, I will pay a cost in terms of probability for the divergence. And so the family of amplification contexts will not give the trivialization, because we don't have we have a term that converges to 1, a term that converges to 0, and so.
Okay, interesting.
Okay.
Thanks.
Thank you.
Okay, let's thank the speaker again. Okay, and next up in a moment, we'll have Jack Senzak speaking on nominal semantics of first-class automatic differentiation.
Alrighty. Alright. Hello everyone, my name is Jack Sunzak. I'm a first-year PhD student at Yale University, and today I'll be presenting some joint work with Alex Lev on nominal semantics of first-class automatic differentiation. Okay, so first of all, what is first-class AD? Well, automatic differentiation, or AD, usually appears as a top-level program transformation. And what I mean by that is it acts as a compiler, taking some source program that denotes a differentiable function and transforming it into a new program that denotes the appropriate derivative. And you can query this new program to recover values of the original program's derivative. Now, in contrast, first-class AD offers differentiation as a first-class programming construct. And what that means is I can write programs that arbitrarily nest and compute derivatives. So here's a lambda expression that takes in a real-to-real function and computes its second derivative at 100. Now, because this is just a lambda, I can evaluate it at a well-typed argument, such as the function that takes in x and multiplies it by 8, and I'll get back an actual program value that represents that derivative computation. So clearly, first-class AD is a lot more expressive than top-level AD, and it turns out, if you look in the machine learning literature, whether it's hyperparameter tuning or meta-learning or even in application areas like cognitive science, there's a variety of situations, both in theory and practice, where it's convenient to compute first-class derivatives. Now, in this talk, I want to talk about a particular implementation strategy that's popular for implementing first-class AD with dual numbers. Okay, so ordinarily, the way that you implement AD using standard dual numbers at the top level is you take some source program, again, denoting a differentiable function, and you fix a value of its derivative that you're interested in computing. So in this example, say 8. And you apply a program transformation that lifts this program to, instead of operating over real numbers, it'll now operate over dual numbers. And each one of these dual numbers, you can think about it as a tuple consisting of the value of a function at some point and the value of its derivative at that same point. And here I write it as a formal sum where we're using epsilon to track the derivative. Now, all of the primitives in this lifted program also operate over dual numbers. And the way that they do this is they act on the normal component of each dual number just like they normally would with real numbers. So for multiplication, for instance, it would be real number multiplication. But on the dual component, it'll actually implement the appropriate rule of calculus, so the product rule. And if I run this program, you can see this in action. So I'll substitute, and then I multiply, and I get back a term that's of the form 8 squared plus 2a epsilon. And you'll notice this is the value of our original function plus its derivative times epsilon. So we can recover the value of the derivative that we were interested in by just taking the coefficient of epsilon. And this is the general recipe. Now, how do you implement first-class AD? Well, to show you why standard dual numbers don't work, suppose we have a differentiation operator that first class applies standard dual number AD each time it's run. Now, before I show you why this doesn't work, we should think about what this program's actually supposed to equal. So if you look at this inner term here, what this is saying is we're computing the partial derivative with respect to y of the function x plus y. So that should equal 1. And if we black box that term as 1 and consider the outer term, we're computing the derivative of just the identity function. And again, that should be 1. So we want this whole program to equal 1. But when I run it, you'll notice that we get 2. And what's going on here is the first time that I evaluate diff, I'm using this epsilon to track the partial derivative with respect to x. Now, the second time that I run diff, I'm also using epsilon to track the partial derivative with respect to y. Now, because these two epsilons end up being in the same scope, the coefficients get combined into a value that's neither the derivative with respect to x or the derivative with respect to y. And this is a general phenomenon called perturbation confusion.
And it turns out that there's actually an algorithm that gets around this. And the way that that works is we'll consider the same example, but now when I run diff, I'm going to use tagged epsilons. And what this will achieve is it's going to keep all of these derivative computations separate. So now as I continue running the program, and I call the second differentiation, I'll use a fresh tagged epsilon. So now when these two epsilons are in the same scope, they'll stay separate, right, as you can see, and we'll actually extract the correct value of the derivative with respect to y. And this leads us to ultimately get the right answer. So this algorithm that I just showed you is very popular. It was introduced by Siske and Perlmutter in 2005 in their landmark paper on perturbation confusion. And over the years, it's been implemented by various systems, including JAX and a beta version of PyTorch and Julia diff. But in 2019, the same authors of the original algorithm realized that there's actually a subtle bug in most implementations. And they ended this paper with this statement, which more or less says that we can't actually be sure any of these highly used popular systems are actually doing the right thing, because, well, to this day, there's no real proof of correctness of this algorithm. Now, I want to talk about how we formalized a version of this algorithm, and how that correctness proof goes. So the general structure of this proof is going to look like this. So we'll start with some source language that's more or less lambda calculus with first-class differentiation. And we're going to interpret it in a way that diff is actually going to correspond to mathematical differentiation. Now, this will tell us what diff should mean, but it's not going to tell us how to implement diff. To actually implement diff, we'll compile this language to a language with name generation. And we need name generation, essentially, to be able to generate these fresh formal infinitesimals for the tagged forward mode algorithm. So once we have this target language, we'll interpret it in a suitable semantics. And then finally, we'll show that these two things are related in a way that shows that tagged forward mode correctly implements differentiation. OK, so because the left side of this picture is pretty standard, I'll start with this. So what is this source language? Well, here's its syntax. As I said, this is a simply typed lambda calculus, but the things to look out here for are it has real numbers, it has smooth primitives like plus or minus, and it also has real constants like 0, 1, 2. But it also has first-class diff. And because we want first-class diff to actually mean mathematical differentiation, that principle is going to guide how we design the semantics for this language. So semantics-wise, types, real will actually be interpreted as real numbers. Products will be interpreted as product spaces. Functions will be interpreted in a suitable notion of function space. And for terms, if all of these primitives in your language are actually smooth, then lambdas will correspond exactly to smooth functions. And differentiation can actually be the function that sends each smooth R to R function to its first order derivative. Now, that covers this side of the picture. So how do we compile this to a language with name generation? Well, the first thing that I have to tell you is what this target language actually looks like. So here's its syntax. It's got a type for dual numbers and real constants that can be used as dual numbers in a trivial sense. It also has names, and it has a monad for representing the effect of name generation. Now, it also has a piece of syntax that's going to let us generate these fresh tags, and a piece of syntax that can coerce those tags into formal infinitesimals epsilon. Now, in order to extract those, we'll also have an operation that takes the coefficient of some particular epsilon by giving it its tag and some dual number that we're interested in. Now, the semantics of name generation is a very well-studied thing. There's a variety of different semantic models we could choose. We opted for a particular one called the Shanuel topos. Intuitively, though, this thing contains mappings for each finite set of tags. You give me a set of values that depend on those tags. So, for example, the way that we'll interpret names is given some set of tags, the set of values that depend on those tags are exactly the same. Same for dual numbers. If we have some set of tags x, we can interpret dual numbers over those tags as formal sums that use infinitesimals in that set. All right, so how do we define this compiler? Well, the idea here is if we start with some source program, it can have an arbitrary type, and we don't know how many times it calls diff. So because we're going to use name generation to implement diff, we need our target program to always be monadic. For types, we'll interpret real numbers as dual numbers and functions as effectful for the same reason as before. Terms also mostly say the same. But here's the interesting part. For tagged forward mode, what we'll do is we'll implement a function that takes in a function and gives you back a new one that is its derivative. What's going on here is we generate a fresh tag, and then we call f with what should be x plus epsilon with that tag, and then we recover that derivative value that we were interested in. Now, that shows you what this side of the picture is. What's like the punchline? What's the correctness guarantee that we get here? So we have this short correctness theorem, even though we're considering a complicated algorithm. And the way you interpret this is, if I have some term with type real that denotes a real number, the compiled version of this program is going to be equal to return of that number. So that means two things. We compute the same real number, implementing differentiation using this tagged forward mode algorithm, but also that number we return doesn't depend on any of the names that were generated throughout the program's runtime. So here's some proof notes. It's pretty dense, but we proved this by logical relations, and we eventually used some different techniques. And if you want to know more about that, come find me at the poster session. But that brings me to the end of my talk.
Yeah, thank you. Are there any questions? And in the meantime, if the next speaker could please start getting set up. There's also some seats in the front if people want to sit down.
Thanks for the talk. You mentioned that the original algorithm had a subtle bug. Is that like, does this formalism like easily capture that? Did you try formalizing the initial like algorithm incorrectly, or?
So the original algorithm had a bug because it allows you to differentiate any program that has real numbers in the domain. So it can be over function spaces, it can be over anything. This one restricts you to just have R to R. But you can still write programs that have like a higher dimensional domain or codomain if you write the lambdas correctly. So I think just because we cleared it down, it made the proof easier and kind of eliminated that bug.
And was that the solution they came up with as well?
So they, I'm not actually sure on the details, but.
Thank you very much for the talk. One quick question, and maybe you hinted at the solution at the last slide, but is any of your development reapplicable for backpropagation?
Yeah, so for backpropagation, this is all forward mode. We are interested in understanding if JAX's reverse mode can be described in a similar way. There's a paper that shows you how reverse mode can be implemented, reverse mode can be implemented as the transpose of forward mode. So we're not sure, but maybe.
Thanks.
Thanks. Yeah, I'm trying to get full screen, but I can't remember. What's the keyboard for that? Just for the transition. Sorry.
The bottom F. Yeah. Okay, so in a moment we're going to have Hugo Paquet speaking on semantic foundations for laziness in discrete probabilistic programming. Also, a note for people, not now, but when the session is done, please put up your posters if you haven't already, but please wait until the end of the session.
Okay, thanks, Cameron. Yes, so this is joint work with Simon Castellan and Tom Irschowitz. Simon is here in the room. So let me just start by explaining a bit the context for this project. There is this large project called Bottascopia, which is led by Simon and based here in Rennes, actually, at INRIA. And it's a project that involves computer scientists, but also plant scientists, and also people who are not academics, who so there are organizations that work with kids, there are organizations who care about more practical aspects of plant science. So what the project is they are building and maintaining a large database of plant species, which is structured in a particular way. And then from this database, they are building tools to automatically generate things like teaching materials or activities for kids or identification activities for people. But so overall, the goal is really to get people to engage more with specific features of plants and really understand how to compare species and so on. So these are the applications. I won't talk about that, but I'll talk a bit more about the I suppose the database aspect and the structure of it, which is related to probabilistic programming. So here's an example I made up. You have a type, so this is a type, this is not a species, it's a type of species called flower with a record type. It has color, size, and season with possible values for each of them. And once you have a type of species, once you have a type, you can write a species. So my species would be a probability distribution, so a probabilistic term of this type. I'll give you an example. So the color is randomly either blue or red with a probability. The size is similarly either small, medium, or large with a certain probability, so you write a program. And the season is deterministically winter. So this is probabilistic, and this corresponds to something called species polymorphism in botany, where two individuals in a given species can have different traits, and so there's an understanding that it's not all individuals are exactly the same. So if you understand this probabilistic program as a distribution, of course it's a distribution over this large algebraic data type, and so you can represent it naively in this way, right? Values and probability coefficients. Or you can represent it slightly differently in this way, observing that each component is defined independently in this case, and so I can define each component of the record type as a kind of probabilistic tree where there are Boolean variables that are corresponding to the flips with a certain bias, and then output values depending on the value of these variables. Now, this is one possible way to implement flowers, but in applications of the Bottascopia project, sometimes they care about other ways to represent the same type of species. And so there might be a simpler kind of representation for flowers, which just remembers the color and the size, and the size can only be small or large. So we're going to care about ways to translate from one representation to the next. So there's there's probably many possible translations, but one is to just get rid of the season field, and then depending on the size, so obviously if it's small or large, you can keep it as small or large, but if it's medium, maybe you randomly say it's small or large. And this probabilistic is not just to be able to talk about probabilistic programming, is because it's important that if a kid is engaging with the tool, then they see a medium-sized plant, they might half the time say it's large, half the time say it's small. So it's important to care about both options. So you write a probabilistic translation, which I hope you can see is a probabilistic program. So it doesn't really matter how I implement it, but it's just what I said. It's a program of this type. And so what's interesting is to look at the ways to compute, so the method for computing the translation of a given species, depending on the representation that you choose. So of course, if you choose the naive representation, the only way to compute the translation is just enumerate over all the possible values, apply the program, and just reorganize the distribution. If you start with this representation, it's a little bit easier. You just get rid of the winter field, and then because I said that when it's medium, it becomes small or large with probability of half, you kind of expand the tree with a new random variable, and then you reorganize the structure so that there's only one path to small, one output node for small and one for large. Okay, you might recognize this as this idea called knowledge compilation. This is a binary decision diagram valued in a particular set. And it's, I think, a more broadly known idea, but the most popular instance of this kind of knowledge compilation is in the DICE language, which from a few years ago. So I think that's maybe the most well-known implementation in this community. And what we did in this work was to understand knowledge compilation as a particular evaluation strategy. So there are two main ideas. The first idea is to realize that sampling is actually two effects, or at least you can see it as a composition of two effects. First, generating a new random variable, and then later on reading the value of the variable you've generated. Okay. So this is not our idea, so a few people have taken this seriously already, including at Lafi last year. The second idea, I think is new, although I'm interested if you've seen it somewhere else, is to decouple these two effects and evaluate one in call by value and the other one in call by name. And I'll try to explain on one example why this is the right thing to do. So look at this simple program. It samples a Boolean variable and just returns the pair of the duplicated pair. So really in probabilistic programming, this should always return either 0, 0 or 1, 1. But that's not really the BDD, the knowledge compilation representation. You would really have a pair in DICE, for example. You would have a pair of BDDs. But what's important is that the Boolean variable that appears in each of these diagrams is the same, right? If this one gives 0, this one also gives 0. Okay, so why does this correspond to this? If I was doing both effects in call by value, I would just have one variable and one single diagram with one probabilistic choice, and then at the end a pair 0, 0 or 1, 1. If I was doing it both in call by name, I would have two diagrams like this, but the variables would be independent, so there would be no correlation between the two copies. So this is really what's going on. And we tried to explain this using standard semantics methods. So nothing really is new. So there are two monads. One monad is for name generation. One monad is for reading the value of the variables you've generated. The name generation monad is exactly the one that appeared in the previous talk, although it's a slightly different base category, but really is the same idea. What's important for these monads is that the semantics is indexed by a finite set of variables, so you want to keep track of the variables you've generated so far in the execution. And then you just apply really the standard thing. So if you haven't seen this before, it might look a bit cryptic, but really, given a monad, there are standard ways to interpret call by name and call by value. So that's what happens. You have a call by value model for name generation, call by name model for reading. And we came up with this kind of way to combine them based on the distributive law, which is a standard way to combine monads. So it gives you a kind of hybrid model where the types are kind of call by name types. That's why the types are diagrams. And the terms are more like call by value with respect to name generation, the same as here. I'll say just to illustrate what's happening here, if you don't understand this. So you have to understand each type as essentially a set of kind of layered decision diagrams, which give you situations like this. So I think this is exactly what happens in knowledge compilation. So, but the point is really it comes for free from this semantic model and these well-known ideas. So for some types, you create a new layer by saying I read, and then depending on the value of the variables, I return either a diagram for the left or a diagram for the right. And this should be a times. For product types, you just return a pair of diagrams. But they're over the same set of variables, which is why you can have correlations. Okay, so just briefly, so R is implemented in call by name, but this gives you the same as call by value because R is essentially doing nothing. It's just reading the state, and it doesn't matter what order you do it in. It's a very kind of a benign effect. And so essentially call by name is equal to call by value, which is why this model gives you the same in a precise sense as the usual call by value semantics of probabilistic programming. Okay, So just to summarize, knowledge compilation can be seen as an evaluation order where you decouple the effect into two effects, and one's in call by value, one's in call by name. And I think generally it gives you a new perspective on call by need more generally, maybe for other effects or for other kinds of types. Okay, I'll stop. Thanks.
Thank you. We have time for a question or two. Yeah, please set up.
Thanks for the talk. So can your framework support higher order and bounded loops, control flow, and things like that? Maybe you said it and I missed it, but.
Yeah, so control flow as in branching, yes, because you have coproducts, some types. But we haven't done recursion. I think recursion would be maybe the easiest. High order is it's not just a tree, right? There's going to be functions at each level, so it's easy. But thanks.
One of the cool things about lazy people is that you can generate like elements of a type that depend on like infinitely many random values. But it seems like if your name generation is called by value here, you wouldn't be able to do that because you could be lazy about reading from the infinitely many, but you still need to like allocate infinitely many names in order to do that. Does it still work? Like, can you still sample a Brownian motion?
Lazy people, there is some call by need happening, right? Because even though you're depending on some of this kind of encoding is happening in Haskell behind the scene. So maybe it's hidden in a different place in a way. But I'd love to understand.
Yeah, let's thank the speaker again. Okay, and after we get set up, we'll have Fabian Seiser about speaking about incremental density computation for efficient programmable inference.
Thanks. All right. So what I'm presenting today is joint work with Jack and Alex, who are here, and with Kash. And to start with, I want to show you a little illustrative example. So suppose you have some data points like these, and it looks like they come from two different clusters. And now suppose you want to infer the latent clusters from this observed data. So you want to get to this ground truth here. One way you could do this is to write a generative model in a probabilistic programming language. So this might look something like this, where you have some prior distribution, which I didn't specify, for the parameters for the clusters. And then you sample two parameters, one for each cluster from the prior. Then you sample cluster assignments for each data point from 1 to n from a Bernoulli distribution. And finally, you sample the actual data points from a normal distribution whose parameter depends on the cluster assignment. So if you run this program, it will generate data sets like the one I showed at the start. But what we want to do in practice is, of course, given a data set, find out what likely parameters led to this data set. So we want to do inference. We want to find execution traces that make the data likely. And what does likely mean? Well, it means we want to find traces that have a high density. And the density function is just basically multiplying together all the probability density functions of the distributions we sampled from. So how do we actually find good traces? One approach might be the following. So in Markov-Chain Monte Carlo, we start with a random initial trace, which does not explain the data very well. So you can see from the visualization it doesn't really fit.
and also the log density is quite high, quite low, sorry. And then we try to improve it step by step. So if we want to draw L samples, we're going to have a loop here, and then make changes to the initial trace. So first of all, we might reassign the data points to different clusters. So we look at each data point and consider switching it to the other cluster. And we do that depending on the density of the changed assignment. So you could do like GIP sampling here, or also an accept reject step. And after we've done all this, we also want to update the parameters based on the new assignment. And we keep going with this. So what you might have noticed here is that we have to evaluate the density function many, many times, and also typically on very similar traces. So doing this naively is kind of wasteful. So if you do this in a naive way, you get quadratic scaling here, which you can see here. But if we're smart about this and compute this incrementally, we get a much gentler slope like here in the data size. So for this simple example, it's kind of not a problem to do this by hand, but for more complex models, you wouldn't want to do this because it's very easy to make mistakes. So we want to automate this. And there's a couple of challenges with doing this that existing systems have encountered. So first thing is, how do we actually represent changes? So here we're in a setting where the user can write an inference program. So the user can basically decide what changes are proposed, and the system does not control this. Also, we want to support a broad range of possible trace updates. For example, splitting or merging clusters in more complex models, or in open universe models, we might want to add or delete objects or entities. We might want to modify subtrees of an AST, like in Maddie's talk on program synthesis, or might want to do gradient-based parameter updates. And we want to represent all of these kinds of changes in a concise and efficient way. And just to give an example of what could go wrong, in many systems, existing systems, if you delete an object in an open universe model, this leads to all kinds of indices being shifted around, and that kind of blows up the change representation. And we want to avoid that. So the second challenge is how to actually automate this in an efficient and correct way. So ideally, we want to achieve the same asymptotic scaling as a manual incrementalization. And for this, we're probably going to have to reuse intermediate results. How exactly are we going to use these? We might organize them in caches, but how do we thread all these caches around the program? And most importantly, how do we reason about the correctness of this whole mess? So our approach for dealing with this is the following. So one key realization regarding the change representation is that the kinds of changes we want to make really depend on what kind of data it is. And this is why we go for a type-driven approach. In particular, we use trace types, which have been mentioned in another talk before already, which have been used for other purposes in the past already. And we're going to combine that with another kind of types, which are change types. So these were introduced in the incremental lambda calculus. And yeah, these two kinds of types have been used before, but we combine them in our framework. So what are trace types? Well, trace types track what random choices a probabilistic program can possibly make during its execution and organizes that in a data structure. And the data structure also reflects the control flow of the program. So if we just have sequential samples in a program, that'll be recorded as a record. So we have this kind of record type with labeled fields. If we have a loop from 1 to n, then the trace type of this will be a list. And in our work, we actually also have a construct for exchangeable sequences. So we can also iterate about a set. And in that case, the trace will be an unordered collection, like a map. And when you actually write a model, you're going to annotate this with a type. So prop just says it's a probabilistic computation, and it has a result type, as usual, but it's also annotated with this trace type here. So this is the example from the start. And this trace type kind of fixes the type of the values that inference algorithms will make changes to. So this is the first ingredient, and the second ingredient is change types. So those describe the changes that values of a certain type can have. For example, for basic types, we might just have a replacement change, just tells you whether it's the same as before and what the new value is. For record types, we'll just have subrecords, which include just the fields that changed and their changes. And for lists, we might just record removals, insertions, and modifications. And the inference programs that the user writes are actually going to generate such change descriptions, which are change types of trace types. As an example, if we have this kind of trace where we have a number of objects with certain positions, and we want to remove the first object, then the change will look something like this, where the number of objects is not the same as before and is now 2, and the first index of the positions list was removed. And this is kind of a smaller change than if all the indices shift around. Okay, so how do we actually do correct and efficient automation? Well, doing this correctly is difficult because in a probabilistic program you have random dependencies for variables, and even some variables might exist only in some branches stochastically. So we decompose this into 2 stages. The first one takes the probabilistic program with a generative model and turns it into a fully deterministic density function. And as a second step, this deterministic program is incrementalized to an incremental updater, which is then used by the inference program. So yeah, in the first step, we take this probabilistic model with a prop type, and turn it into a density function, which takes the trace as input, returns the result, and also the weight, or the density. So this kind of transformation is usually routine, but in our setting it's a bit more subtle, because we have these exchangeable sequences and name generations, which makes this a bit more complicated. If you're curious, talk to us in the poster session. The second stage is the actual incrementalization. So this is inspired by the incremental lambda calculus. And the idea is that we have a deterministic program from inputs to outputs, and the incremental version, in addition, also produces an updater from input changes to output changes. So this updater is a co-inductive type, which looks something like this. So it's essentially a function from input changes to output changes plus a new updater for subsequent changes. And this kind of packages up and encapsulates the caches for intermediate results, which we need for faster incremental updates. How do we actually produce these updaters? Well, for primitives, they just have their own specific updater versions, and the translation rules for the transformation compose them together. We have correctness proofs for these transformations based on denotational semantics and logical relations. And we also have a prototype implementation where we compared this to a non-incremental version and to Gen's incrementalization on a couple of models that are kind of challenging. And we implemented a couple of MPMC kernels. And the takeaway is that our method in blue is the only one that achieves the desired asymptotic scaling in the data size for all models and kernels. Yeah. Thanks for listening, and look forward to questions.
Thank you. We have time for a question or two. And could the next speaker please come up? You can plug in.
Thank you for the talk. I'm just interested in what is the expensive part of your original computation? Is it really a lot of the same computation happens, or you have to then you can just directly reuse the intermediate results, or you also have to perform different kind of computations in the incrementalization
Okay, so in a moment we'll have the final talk of this session by Dominik Geisler, speaking about probabilistic programming, meeting automata theory with exact inference using weighted automata. And once again, if you don't have your poster up yet, please do so during the break. So following this, we'll have about a half-hour break, and then we'll be back. Any announcements about how the afternoon will work?
I'd also just remember, if you didn't in the morning, to RSVP for the Basis event. The link is on the Lafi website at the bottom of the description.
There's still space, as far as you know.
And as far as I know, there's still space, yeah.
Familiar with them as a generalized version of the well-known finite automata. Furthermore, we provide a framework which allows for manipulation of these weighted automata in such a way that the underlying probability distribution will be modified such that the semantics of the program statement affects the distribution. Again, we will see an example later on. And we do this by using very basic automata theoretic operations such as the sequential composition of automata or intersection. And lastly, I won't talk about this today. If you're interested, you can, of course, ask afterwards or come through my poster over there. But we also proved the soundness with respect to pre-existing operation semantics as introduced here. Okay, first I would like to introduce the model. So you are all on the same, or we are all on the same page. First, the general idea is we want to model these probability distributions as weighted automata, and therefore our program semantics transforms these weighted automata in such a way that the effects are modeled as these basic automata theoretic operations. So here we have a simple weighted automaton. We can already see the difference between weighted automata and the more generally known finite automata. We, for instance, have this 1/2 here, right? So we have weights attached to initial and final states. Here, if I omit a weight, this just means the weight is equal to 1. And we also have this 1/2 x here, which is also something we would not be able to see very often. So how do we now evaluate these weighted automata, or what do they mean? Well, you can think of these weighted automata generally as a weighted multi-counter system, where for each program variable we introduce one such symbol here. So here in this case, since we only have one symbol, this model is a univariate distribution. And every time we take a transition with a corresponding symbol, we increment the counter by 1. We do not allow any decrementation, only increments by 1. And at the end, if we reach a final state, then we basically see what is the value of the counter. This corresponds to the program variable's valuation, and the coefficient, so the multiplication of all the weights, corresponds to the probability that the state occurs. So here we can see the probability distribution that is encoded by this automaton here. It's just a geometric distribution, and since the slide is for finite space, I can't display the whole distribution, but this goes on for infinity, so this is an infinite support distribution. And let me just walk you through one case here. Right, this x-axis encodes, or x-axis indicates the values of the program variable associated with x, and the y-axis the probability of the state occurring. So here, for instance, we have x as the value of 0. This corresponds to this run here, right? We start and then we directly terminate. We do not take any x transitions, therefore x is never incremented and stays at 0. And we have the coefficient of 1/2, so here we have 50%. Okay, what can we now do with these weighted automata? Well, we can now apply a very basic operation, such as we can add another automaton to the end of it. Here, in this case, we add another x transition, and this results in a shift on our distribution, right? So we basically increment by 1. What we also can do is we, for instance, and this is very important, we can weight the whole automaton, so we scale down the distribution. Therefore, we can also handle subdistributions here. But now I want to talk about the semantics, and therefore I will switch the topic really quick, and I will talk about fish. Some of you might be familiar with the goldfish piranha problem. If you're not, I will briefly introduce it. So we have two protagonists. We have the goldfish and we have the piranha. And we also have our location, namely the fishbowl. but since we are dealing with probabilities and uncertainty here, we paint this fishbowl black so we cannot see anything. Now, at the start of this problem, we have our fishbowl. Remember, we painted it black for some reason, so we cannot see anything, but we know that there's one fish inside. And we know that it is either a goldfish with probability 1/2 or a piranha with probability 1/2. Now what we do is we throw another piranha inside, and right before any of the fish may attack each other, we just remove one fish, and this happens to be a piranha. Now, the question here is, what is the probability that we start with a piranha given that we remove one at the end after following all these steps? And yeah, since this is my talk, I want to apply our automata theoretic construction in order to resolve this question. Okay, so for this, we first need to model this as a probabilistic program, a very simple one. Here we have two variables p and r, and the values are 0 and 1, where 0 stands for goldfish and 1 stands for piranha. So here we flip a coin, and based on the outcome, p is either 0, so there's a goldfish inside, or 1, so there's a piranha inside. If p is equal to 1, so if there's a piranha inside, then we throw another piranha in, and we remove one fish directly, so therefore we remove a piranha with probability 1. And in the other case, we just throw a coin again. And at the end, we observe that we have removed a piranha in fact. So what we also assume is that all variables have the value of 0 initially. Now, I want to show you how these semantics work. On the left-hand side, we can see the program. On the right-hand side, the current automaton. Here, this is the automaton which represents our assumption, namely that every variable has the value of 0 initially. Okay, let's start. First, we sample p from the Bernoulli distribution, and we have defined some distributions which can be used in our inference. For instance, here, this is how the automaton for the Bernoulli distribution looks like. Let's walk through it real quick. We have two paths here, right? This one, we don't take any p transitions, therefore p has the value of 0, and the weight is 1/2, so the probability is 1/2. And this path here, we take one p transition, the probability is the same, so we have 50% p is 0, 50% p is 1. Okay, what we would expect. Now, the next part is a bit more interesting. Here we want to filter based on the value of p, and we want to basically split the automaton into two. One where every path satisfies this guard, namely we take exactly one p transition, and one where no path in the automaton satisfies this guard, so there's no path which has exactly one p transition. Here, since we only have two, it is very simple. We split it up into two, and now we have two separate automata on which we apply the semantics for the then branch here or the else branch respectively. So for this case, we set r to 1. Remember, we just, since our multi-counter the multi-counter system part, we just add another r transition here to the end. So we set r to 1. And then we're done with this case. And for the second case, we already seen how this geometric distribution, the Bernoulli distribution automaton looks like. So we also just append it to the end. Now we connect it to one automaton again. We are done with this if statement. And now we can briefly check whether it makes sense. So here, in this case, we have with probability 50% a piranha originally inside, and then we remove a piranha certainly. And here, at the start, we have a goldfish inside, and then with 1/2 times 1/2, so 25%, we remove a goldfish, and 1/2 times 1/2, so 25%, we remove a piranha. Okay. Now at the end, we observe that we have removed a piranha. Therefore, we now want to remove every path where we do not take exactly one R transition. And here in this case, this is only this path here, right? And therefore, what we do is we remove this final state at the bottom. Okay, now we are almost done. However, what we now have is the unnormalized posterior distribution. So we have a subdistribution since we have removed probability mass, and now we want to normalize this again. So therefore, we compute the probability mass of this automaton. We've shown in our publication that this is possible in polynomial time. And then we normalize or weight the whole automaton by the reciprocal of this. And now we're done. We have the normalized posterior distribution, which has a probability mass of 1 again. And we can answer our question. So what is the probability that we start with a piranha, given that we remove one at the end? And if we remember our encoding, here we have p is equal to 1, right? And on this path, so this is the path that represents that we start with a piranha, we just have to calculate the probability mass here. So we have to multiply 4/3 times 1/2, and this is equal to 2/3, which is the answer to this problem. Okay, I want to summarize. What we have done is we have provided a sound framework for exact inference using these weighted automata and the basic automata theoretic operations. What is for future work? We want to relax some syntactic restrictions. So for instance, on the expressivity of the guards that we use. We also want to use more expressive automata models, such as push-down automata or their variants, to also model more complex distributions or more complex guards. And lastly, we want to add tool support so we can infer all these rules automatically. So if you're interested, here is the paper to this brief talk, and right here is my poster. So if you're interested, you can find me at the poster session or just in the break after this talk. And I thank you very much for your attention.
Thank you. Do we have any questions?
Thanks for the talk. I was wondering if you can characterize the kinds of distributions that these automata can express.
Yeah, that's a very good question. So what we haven't done yet is that we characterize exactly the set of PGA, also the automata called PGA, so the kinds of distributions that this automaton can actually represent. So this is something that we left for future work.
Okay.
Okay, well, let's thank the speaker again. And we'll resume in half an hour. There will be a few more talks and then the poster session. There's a break in the same room as before.
We can start the last session of the day. And to start with, we have Andy Gordon, who is going to talk about multi-agent system for traceable Bayesian workflow.
Great, thanks, Guillaume. Great to see everyone. This is joint work with Hong Gay at University of Cambridge and our student Zianda Sun. Zianda Sun couldn't be here today, but he's on WhatsApp and he's watching the live stream. So he's my backup if I can't answer your questions. Great. So what is this about? What's the motivation? Basically, we want to solve Bayesian modeling and automate the Bayesian workflow. So we today, if like a scientist scientist, a social scientist, computer scientist, whatever, you've got a bit of data, you want to do a Bayesian analysis of it. Today, this is pretty hard. There's a lot of iteration. If you're not an expert, there's a lot of pitfalls. We wanted to see if we could automate that. To some extent, probabilistic programming languages have always been trying to do this, but there's a number of things like checking good fit of the model and a whole bunch of things, choice of model, that are sort of outside the scope of the core probabilistic programming language itself. So we're trying to use prompts to large language models as a sort of language for inference to describe the whole process of doing Bayesian modeling. So we're going to be formalizing this kind of loop. So what we're going to do is build a multi-agent system that orchestrates existing tools. We behind the scenes, but I'm not going to show you any of its code, we use Stan as a probabilistic modeling language. But we use a whole lot of other tools as well to visualize the data and to look at sort of analyze the fits of the model against the data and so forth. All these kind of steps we want to orchestrate, and we get two outputs. One is we get a model that passes validation checks on the data we've given it and work well predictively. And also we get exploration traces, so we get a long trace of all the work that the machine has been doing while following our prompts as it tries to follow through on the Bayesian workflow. And this trace documents models that were considered failures and revisions. And that's what we do. And we think we're the first to do this, and we think it's an important thing to do, as you'll hear. So firstly, what do we mean by an agent? I'm finding at POPL some people know about agents, some people do not. For those who don't, so AI's been around for a while. GitHub Copilot came out 3-4 years ago, and it was like AI autocomplete. As you know, you type some stuff and it would autocomplete the rest of your sentence when you were writing code. Since then, and particularly last year, a lot of the energy is around what are called AI agents. And they have some kind of agency, meaning they've got an ability to perceive their environment, reason about a goal that you've given it, and then to perform multiple step actions using tools. And this is, there's a group in London that hosts something called the AI Native Dev Landscape, and a great website that is a kind of roadmap, a landscape of lots of different AI tools that are being developed in academia and in industry. And this is a screenshot of different AI agents. I think there's 124 on their roadmap, but I'm highlighting some of the famous ones. So the one that maybe is most famous just at the moment is Claude Code from Anthropic. There's also Codex CLI from OpenAI, and there's Gemini and Google Anti-Gravity, from Google, and a whole lot of other ones. So these tools, you basically give them a command, and then they'll execute a while. And they can issue shell commands. They can issue a bunch of things to get some work done. I am completely losing track of time. How long do I have to go? We still have 5 minutes. 5 minutes, okay. So this is a diagram of what we build. So it's like a loop. This is what you go through when you do Bayesian workflow. You start off by doing exploratory data analysis, and in our prompt we tell the AI agent to test at least 2 to 3 competing hypotheses. This is what we put into the prompt, right? We don't write code to do this, we put it as a prompt. And then there's a design phase, and we'll say, for example, explicitly state what evidence would make you abandon each model. So we're getting it to be critical as well as designing models, and it builds a little ladder of models it wants to try. And then it goes into a loop where it tries to apply these models. And given a model, it does a number of checks. It does a prior check. It checks that the data generated from the prior has plausible scale and support. It also tries to simulate data from the model with known parameters and then sees if model fitting can actually recover those parameters. And if these fail, sometimes it will try and adjust, it kind of loops and will try and adjust them. Other times it just throws away that model saying it doesn't work well. We'll have to try another thing. And then it does fitting, and it runs various convergence diagnostics, builds trace plots and so forth. And this is, remember I said the key thing of our method is we generate a trace of what we've developed. And these kinds of diagnostics, the plots and so forth, get dropped into this trace. So we're building up evidence of what we've done. And this is evidence that is looked at by the model. The model is aware of it. So as it goes around the loop, it can look at previous work that's happened. So it makes better decisions that way. And then it finally has an evaluation where we run posterior predictive checks to see how well the model can generate predictions of known observed data. So that's the main loop, and as I say, it generates an exploration trace. And finally, green at the end, we produce a synthesis report that is the end of it. It's the report back to the person on how the data analysis has gone. Why is it multi-agent? Basically, because it doesn't work if you just ask it to do Bayesian workflow in one prompt. You've got to break it down into multiple prompts, and I don't have time to really elaborate that. It works much better if you break it down into prompts. This is a program, right? This is all the code that we've written, as it were, that defines the Bayesian workflow, and it's a bunch of markdown files. Okay, it's not. That's why I'm saying it's 1,228 lines of prompt. So this is programming in natural language, right? As a collection of markdown files, and some of them are agents, and some of them are skills, which is particular jargon that Claude has for basically subroutines that the model can call to get work down. And yeah, that's the gist of that. I've got an example. So this is the system prompt. It starts off saying you are an autonomous technical agent specializing in Bayesian modeling, statistical computing, and software engineering. And this goes on for hundreds of lines. I wanted to give you a gist of what it was, so I put it into Claude and say, summarize this, for a presentation, until Claude came back with this, which is its summary of that. And you can see what we're saying in the system prompt. Like we provide various core principles, tell it about how to use a to-do list, tell it can run parallel sub-agents and so forth. And then basically, or crucially, in red here, we've got 4 phases. I'm not quite sure what happened to 4 and 5. Maybe we can ask Xander. But those are the 4 phases that it performs. That's the loop I was talking about. Very quickly, an example. This is a famous data set of cars with their mileages and their weights and the number of cylinders from the 70s and 80s. And this is an output from the first phase. This is the EDA. We're just getting it to look at the data, literally look at it in the sense of making plots. And in this phase, it's making some hypotheses about what model would well fit it. And basically, it's going to come up with a model that fits this trend here of how the miles per gallon varies versus year. And then again, a key part of our method is that we generate this huge exploration trace. I don't have time or space to show you it, so I asked Claude, give me a summary of what happened in the exploration space, which is what you see on the right there. And basically the gist is, while it did the ADA and it figured out that weight was very important, and it notes some statistical jargon, the severe multi-collinearity, the origin, like where the cars come from, seems to have a large effect. And then during model design, it came up with 9 experiments it wanted to do based on different model classes. There was a simple physical one, and then there were other ones that combined the origin in as well in different ways. And then it ran the modeling. And what happened was that the first class of models was validated, and the other 2 ones were skipped because it found that this apparent origin effect, like as I say, whether it was from Japan, Europe, or the USA, turned out not to be needed once it looked carefully at a simpler model. And then it produced a report. And here's the final model. Sorry, it's a bit small, but it's a simple sort of linear regression where basically the log MPG is being predicted by the weight plus the year. So it does a nice job. We wanted to do a comparison with the closest related work, which is a system called POPL'26. this chart basically is showing that we get very similar performance. The blue points are actually human written reference models. This is a bunch of data sets from Posterior DB, and this is a measure of goodness of fit, and higher is better. And you can see that basically the orange models that have come from our system are actually nearby and sometimes a little bit better than the human written models. We don't, and sometimes it does worse, to be honest. BoxLM also did worse here. It's a little bit hard to completely compare or fairly compare with BoxLM because it's not open source, and they actually used an older model than the one we were using. So I do some details about that, but if you really want the details, please ask me. Here's a summary of a comparison of this compared to earlier work. There was a ton of work on, like, starting with the very famous automatic statistician from about 10 years ago that was trying to automatically generate just models. And they had quite a limited search space, and our more recent work, such as us or BoxLM, are more open-ended, like arbitrary stand models. But the focus of the earlier work was discovery, and it didn't look at traceability. It didn't build up this story of trying out different models and then kind of explaining why you made a decision about the final output. And that's really what's unique to our system. BoxLM did not do that to the same extent. So I will end there. I can't resist putting this up. This is a meme from 3 years ago when just after ChatGPT had come out, and people realized that, or Andrei Karpathy realized that, the hottest new programming language was with English. Well, at Lafi, I'd like to just proclaim that I think the hottest new language for inference is English. So thanks for your attention.
Okay. Any questions? A lot of questions.
Hi, very exciting.
Thank you.
Quick question. Did you folks notice any situations where the LLM fails in the way how it reasons about statistics?
Where it fails to reason about?
Yeah, if there are some spectacular failures of runs.
Yes. I mean, yes. Sorry, I didn't emphasize that. I went quite quickly. In that chart I showed, I think there were 18 orange points, and there were 6 that weren't there where the inference had failed. Like where, say, like I mentioned, various reasons we might reject a model. So those 6 models got rejected. So that definitely happens.
One other quick question.
Do you adjust at all for multiple hypothesis testing? Because, like, if an LLM is testing, like, hundreds or thousands of hypotheses, then, like, the threshold for accepting should probably be different.
What do you mean? What kind of hypothesis testing?
When you do multiple regressions, that in just classical statistics, then you have to.
You mean in non-Bayesian statistics?
Yeah, non-Bayesian statistics. Like you lower your p-values because it's more like when you're testing for tons and tons of things, it's more likely that one of them will just seem true by chance.
Okay, we're not doing sort of classical statistics here. We're very much doing Bayesian statistics.
Sure, but the same phenomenon still happens in Bayesian statistics. I'm fairly sure, just based on like model. Anyways.
Yeah. So we basically ask it to look at the data and come up with the best model it can. And in Bayesian terms, and in fact we don't even give it a hypothesis, so to speak. We get it to generate the hypothesis during the EDA phase. So I think it would be. I think we. Okay, I don't know the details of that, but we get it. The EDA thing gets it to generate the hypotheses, and then after that, it's trying to sort of confirm them. A bit like the hypothesis that we saw, where it thought that it would need to model the origin in the model, but then it figured that was not necessary based on the investigation it did. So I hope that answers your question.
Okay, thanks.
Right. Any other question while we finish the setup?
Oh, yeah.
Have you thought about, or maybe you've already done experiments on this, but on data sets that really it won't have seen Bayesian models of before? like to what extent is it like, oh, I know this model?
That is a great question. I mean, we've evaluated this on fairly simple models, and undoubtedly we could give it a situation that it would be beyond what it could do. We don't have a good evaluation for that yet, but that's an interesting thing to think about. I should say what we're doing. This is, I mean, we're presenting this at Lafi, but we hope to write this up as a proper refereed publication. And so that's, that is a kind of question. How do we kind of measure or evaluate what is the space of models, that or data sets that this is actually good for? And I don't know. We can give examples. I'm not sure how we can empirically, establish that kind of question. And one of the difficulties there is that, of course, these models, if we're working with public models, they may well be part of the training set, and so we have that tainting problem.
Maybe another question for this
Sure.
audience.
Sure.
While they're setting that up, from the perspective of people working on this kind of system, what do you see as the value of having probabilistic programming languages for it to hypothesize these models in, versus, for example, having to write all the inference and modeling code itself? And are there like dream languages that we could have for modeling, or is it already, just use Stan? Like, are there a feature does Claude want a better probabilistic programming language to work with?
Yeah, that is a great question. I mean, obviously my bias is that these things are, probabilistic programming languages, allow you to kind of more compactly express the inference code. So I think that helps humans write inference code, and so that you would think that would also help Claude. We could experiment. Once we've got the system, it's all automatic. So we could. At the moment, it generates Stan, but it's dead easy to get it to say, generate Pyro or Church or some other language, or maybe even just build the inference itself and do just do the MCMC from scratch. We could experiment with those kind of things. When natural language is a programming language, the details of the kind of conventional programming language sort of starts to matter less and less.
Okay. Let's thank Sandy once again. Thank you very much.
Thank you.
And now we have Madhav Konda, who is going to talk about grammar-constrained LLM generation. Okay. Okay, and now we have Maurizio Barbada Costa, who is going to talk about language model probabilistic programming for improving auto-formalization.
All right, thank you for that introduction. My name is Mauricio. This is our work on auto-formalization using language model probabilistic programming. This is joint work with lots of people who are in this room right now. Yeah, so without further ado, I'll start by introducing what auto-formalization is. And to do that, I'm going to start with this example of the Kepler conjecture. In the year 1611, Johann Kepler conjectured that the optimal sphere packing in 3 dimensions is this hexagonal close packing, which is this configuration of balls that kind of shows up in nature pretty often at the grocery store. It's how cannonballs are configured. In 1998, Thomas Hales proved the conjecture. In 2014, the FlySpec project formalized the proof in Isabelle and actually found holes in the proof that had to be revised. And then in 2025, multiple companies are now working on formalizing large swaths of informal math into Lean4 using LLMs. The key word here is formalize. Okay, so what I mean by formalize is this translation task where we're going to start with natural language and convert that into a formal theorem-proving language so that we can defer the certification of some code to a machine as opposed to a person. So auto-formalization is going to be like a pipeline for doing this formalization in a way that involves minimal human intervention. And this is important because humans often make mistakes, right, as we saw in the example, that machines are a little bit more robust to. But this is challenging because natural language is often very underspecified. Natural language has a lot of shorthand and has a lot of abbreviations that have to be spelled out very explicitly for Lean4. Because Lean4 is very pedantic. So if we're going to create an auto-formalization pipeline, one way that we can do this is by using a prompt harness. I should say in the examples or in the different attempts at doing this that I'm going to consider, I'm only considering inference time strategies for doing this, so things that don't involve training. So your first attempt at doing this might be making a prompt harness, right? And this would involve passing many text signals into an LLM, like make the informal statement match the original, do not make mistakes or else, only output lean. But this is challenging, okay, because when you pass multiple of these text signals into the LLM, you could push it into weird parts of its distribution, and you can alter the performance in unpredictable ways. Also, prompting on its own often isn't enough to get lean or an LLM to output correct lean. And this is because sometimes the LM is defiant. It'll intersperse natural language with its lean code output. And oftentimes the lean output that it does make is not well typed. That's because it gets the syntax wrong or because it doesn't pass the type checker and so forth and so on. Your second attempt at making an auto-formalization pipeline might involve locally constrained decoding. And this involves, at every step of the LM generation process, masking the tokens in the vocabulary that otherwise would call the LM to deviate from the target grammar. And so when you use this sampling procedure, the samples that you get fall according to this distribution that I'm calling QLCD. So the notation here is QLLM is the base LM distribution, J is going to be the set of strings that are well typed, and then J bar is the prefixes of all strings that are well typed. The Z's under each of these QLLMs are the normalizing constants that you need in order to adjust for the tokens that you've excised from each of the token generation steps. So the challenge here is that because we're dividing these QLLMs by multiple of these Z's, we're distorting the base distribution QLLM, and this can be quite substantial. And so when you generate samples from QLCD, the probability assigned to those samples by QLLM can potentially be very low, and that's correlated with poor performance in downstream tasks. Now, our third attempt is going to involve using GenLM, which is a language model probabilistic programming framework that's going to allow us to sample from the unnormalized distribution QLLM times phi. Phi is what are known as these potentials, and phi is going to be just a real valued function where we assign some real number to the token sequences that are generated by an LLM. And this is a convenient programming model to have, right? If I wanted to do constrained decoding, what I could do is I could create a potential phi that's going to assign 1 when x is well typed and 0 otherwise. So the challenge about sampling from this distribution directly is that this normalizing constant z is intractable because it involves taking a sum across all of the token sequences that an LLM could produce. However, the advantage of sampling from G is that samples from this distribution are much more closely calibrated with those from the base distribution QLLM. So the workaround that GenLM uses to sample from this distribution is it uses sequential Monte Carlo to generate samples approximately from G as opposed to exactly. And so sequential Monte Carlo is going to go through the following steps. Okay, so if we start with a prefix of an LLM output, we're going to generate multiple candidate extensions of that prefix. We're going to weight these. If I have a binary potential, like one that does constrained decoding, these weights are going to be just 1 or 0. And in general, if the potential was continuous, these weights would correspond to the importance weight. And then we're going to resample proportional to the importance weights that we assign to each of these extensions. And then we're going to repeat this process over and over. So for the particular case of auto-formalization using GenLM, our potential phi is going to be composed of the product of 2 components. The first is going to be phi WT, or phi well-typed, which uses incremental type checking to steer the LLM generation to output well-typed lean code. And the way that we do this is by affixing a dummy conclusion and proof at certain safe checkpoints of the LM generation, and then passing that into the lean4 checker so that we have an incremental type checking signal. And then the second potential that we're going to use, phi CC, or phi cycle consistency, is going to enforce cycle consistency between the informal and formal statements. Cycle consistency is a heuristic that's used in translation that basically says that between 2 translations, the better one is the one whose back translation is more closely similar to the original statement. The way that we're going to encode this as a potential is in the following way. We're going to start with an informal statement. We're going to make a couple formalization attempts. And then we're going to, for each formalization attempt, create a new prompt to an LLM that's going to request that it informalize the formal statement. Phi CC is then going to be assigned the probability of the original informal statement under this informalization prompt. So here's a summary of the pipeline. We're going to start with an informal statement. We're going to make multiple candidate formalizations using GenLM that are steered to be well-typed lean code. And GenLM is also going to upweight the sequences that satisfy cycle consistency. And then finally, in the end, we're going to sample one of the sequences according to its importance weight. And that's going to be our final output of our auto-formalization pipeline. So here are what the results look like. I'm happy to share more details about the benchmarks and about some of our methodology during the poster session. But for now, the big kind of TLDR is we're able to get better accuracy than a baseline using fewer tokens and less time as well. So key takeaways here are that GenLM offers a very convenient programming model for representing these decoding strategies that simply involves defining these potentials. And it's very practical, even in kind of reasonable use cases. So yeah, that's the end of my talk. Thank you.
Any questions? Yeah.
One of your slides shows that you generate a term with the probability of product of that is well typed and the other term. But sometimes if you, maybe the prefix of the term is not well typed, but if you continue, you'll get well typed term. So when did you evaluate if the term is well typed in the generation process? Did that introduce a problem for you?
Yeah, so we do these checks at these safe checkpoints, which happens to be, for instance, after a variable is defined or after like a hypothesis is defined in lean. And that's denoted by like a closed parenthesis, right? And so once you reach an instance of a closed parenthesis, right, you're at kind of some intermediate level of the generation, and we affix a dummy conclusion and a dummy prefix, and that tells us, okay, this, at least everything up to here is well typed, right? So we kind of, so yes, it is possible that if you're, if you have code that's not well typed, it'll eventually salvage to something that's typed, but that doesn't end up being a problem with our use case because we do the constraining at these safe checkpoints. Yep.
A follow-on to that.
Mm-hmm.
Does lean? This is an honest question. I don't know. Does lean complain when you haven't unified meta variables? Because I would imagine, like, if you have your approach where you put in like a trivial statement, then there could be some unification. Like, you could have something that could be well typed, as long as later on you put something in that makes meta variables unify. But without that, it wouldn't be well typed.
Yeah, it does complain about meta variables, and I've seen that be more of a case when you try to do incremental type checking when you're generating proofs. But I have to think a little bit more about this affects creating the specification for a proof as opposed to the proof itself.
Just one last question. So you didn't say what model you were using, because state-of-the-art models are super good at generating lean code right now without constrained decoding. So results are a little bit surprising.
Yeah. So we use a 70B model. So that was like DeepSeek, Llama, and it's from a couple years ago. I imagine the Claude and stuff that's been RLVR'd very heavily on lean can probably do better now. But yeah.
Okay, thanks a lot.
Yeah, thank you.
And I think that concludes the last session of Lafi.